the MIMO systems, visible light communication, and so on. So today he'll be talking about some of the work happening in his group in the area of visible light communication. And also I would like to mention he has many awards to his credit. He got this Varna Jayanti Fellowship and more recently the J.C. Bose National Fellowship. And also he's a fellow of Indian National Academy of Engineers, National Academy of Science, Indian National Science Academy, and Indian Academy of Science. And his book on MIMO, like very large MIMO systems, is very well known and widely referred to. And yeah, with that introduction, I would hand over to Professor Chokkalingam for his presentation.
So thank you, Varun, for the elaborate introduction. And it's nice to be in this workshop. Thank you for having me in this workshop and then allowing me to share some of my research and some views on the visible light wireless communications. So before I start, let me share my, I will mute my video for the sake of bandwidth considerations. So let me mute my video and let me also share my screen now. Okay, I shared my screen or the slides. Can you see my first slide?
Not yet. Yes, now it's visible.
Yeah. Okay, let me make it full size. Okay, so hide this. Okay, I think everyone can see my slides full, I guess. So I think I have about 40 minutes or so to talk, so that 5-10 minutes I can answer some questions later. So what I'm going to talk about is visible light wireless communications and its role in future indoor and vehicular networks. So we know indoor we have Wi-Fi, we have Bluetooth, we have several other personal area networks already, and why one more? So that is one question everybody has, and there are a lot of reasons for it. We will go through some of the key aspects why VLC is important. And likewise, in vehicular communications also, there are several standards and networks, including specific standards for vehicle communications. Now, the role that I will play is just to highlight some of the key issues of VLC under the following topics. Why VLC? And from a communications engineer's point of view, what are the key elements involved? Particularly, I'm interested in looking at how a visible light wireless communication link looks like. And at the transmitter side, you will have a bunch of LEDs to transmit information. At the receiver, you will have a bunch of photodiodes as receivers. So we will talk about those details about what the standards will not say. If you go to a VLC standard, which is 802.15.7, which is for both indoor as well as outdoor specifications, they will give a lot of 5-layer types. What are the several things we will go through in 1 or 2 slides later. But what they will not talk about is how to choose the elements which will constitute the link, which is how to choose a transmitting LED, its specification, and what it affects in terms of rate, modulation, and performance, and so on. Likewise, how to decide using the photodiodes and so on. So we will focus a little on that because that is probably not in very many textbooks in a form that we would like to have. When we started our research in VLC several years back, we wanted to understand as a core requirement of a communication system engineer what he should know about these transmitting and the receiving devices. And we will quickly go through some topics related to VLC standard and maybe highlight on some 5G VLC experiment, which we did not do, but what I saw in the latest literature. And with that, I'll make some concluding remarks. Okay, so we are talking about visible light communications, and we are talking about RF spectrum as well as electromagnetic spectrum in general. And what we are talking about is visible light spectrum here. We have moved from this microwave region all the way to millimetric wave region. And in 6G, we are talking about terahertz communication. So beyond terahertz communication, you have these wavelengths in the infrared, visible light, and ultraviolet. So in that, what we are focusing here right now is visible light. And the idea is spectrum crowding happens a lot in the microwave and even millimetric wave. We expect that things will be overcrowded in the next decade or so. So terahertz is a possibility for 6G, but more importantly, visible light, which is very attractive in several other for several other reasons, is the key. So let us focus on that. So we are talking about optical wireless communication. When I say visible light wireless communication, there is a small chunk of spectrum which is in the visible wavelength range. So we have infrared, visible, and ultraviolet. All are optical or belong to optical band, but we are now focusing primarily on the visible. And when you say optical wireless communication, I think we should roll out the use of guided medium, which is fiber. So we are not talking about LEDs and photodiodes to be used along with fiber, which is a guided medium. We are talking about a free space medium, which is not being guided. So put a radiation of optical nature to convey information. So that's what we are talking about. Now, important thing about this from a generic, resource availability point of view is we are talking about the visible light wavelength range from 700 nanometer to 400 nanometer, which is about 300 nanometer of wavelength available. And if you convert these wavelengths into frequencies, you have 428 terahertz to 750 terahertz. So the difference between these two, the lower mark, which is the red side, and blue side or violet side, you have about 300 terahertz of bandwidth. That is a huge amount of resources. Whether we have the devices technology to make use of the entire bandwidth, we do not have that yet. But notionally, you can view the bandwidth available. Right now, we say millimetric wave, we have about 6 gigahertz of bandwidth, but 7 gigahertz bandwidth, that is too high, is what we think. But imagine in visible light, you have 300 terahertz of bandwidth, and they can be used with a lot of advantages. Particularly, we will focus on indoor and high data rate communication over short distances using LED or laser diodes. So there are two possibilities in the transmitter. Very monochromatic sources of light like laser diodes as the source, as one possible transmitter, or more diffused sources like LEDs, what we use in our household white bulbs, as the transmitter. So there are, I think, maybe one or two talks later focusing on these laser diode based sources, experiments, but I will focus on these white LEDs that we use in our household, how it can be used for VLC, right? And photodiodes as receivers. Okay, so this is the main difference. When you have a RF communication, you have a big investment in terms of hardware development and cost, in terms of creating a baseband to passband conversion, in terms of up conversion, power amplification, and then RF radiation using a transmitter antenna. They are quite expensive and quite involved. And likewise, at the receiver, you will do passband to baseband conversion using down converters and then low noise amplifier and so on and so forth. So it is fairly a complicated thing, but we are having in our hand a cell phone several transceivers in the RF, so it's all practical. It's okay. But the point I'm trying to make is here in VLC we use very simple hardware. Probably the driver circuit is all we have to use, and maybe the transconductor impedance amplifiers at the receiver you may have to build. But generally, it is a very simple architecture. Transmitter is LED, and you modulate the intensity, and generally we call this modulation as intensity modulation, and you don't do any sophisticated detection beyond certain things which are required as direct detection. So IMDD is what we have to do, and they are very simple. Now LEDs and photodiodes have switching times involved, and those are important to decide what is the modulating frequency. So we'll come to that one or two slides later. So these are the pros and cons. I think everybody may probably easily see this. So LEDs and photodiodes are low power, low cost devices, and the visible light spectrum is unlicensed, so there is no cost. And more importantly, light does not interfere with other RF communications in terms of creating EM interference. That is one. And likewise, it is even more resilient to other RF radiations to be interfered with itself. That's where it is non-interference. It is not going to be interfered by other RF radiations. And in closed loop applications like where we are right now, in sitting in our rooms, if you want to communicate using the lights that we are having in front of us or above us, it is going to give inherent security. If you use Wi-Fi, if I use Wi-Fi connection, my Wi-Fi radiation will be visible heard from the street. And if you can break the security, you can snoop in my transmission or reception. So that does not happen in VLC. That is an advantage. And Another important advantage is that white LED has become very popular and it has become very commercial. And the efficiency of the white LED is very high, and everybody is switching over to white LED for lighting purposes. So you ride along with that LED lighting technology. So communication technology rides along with white LED technology. And we can use existing infrastructures like indoor fixtures, light fixtures, street lights, traffic signals, vehicle lights, and displays as sources of communication. And you can obviously, as communication engineers, we can use a lot of cool techniques like MIMO and OFDM to improve the spectral efficiency and performance. And what are the drawbacks? Drawback is probably one thing which will come immediately to our mind is the channel itself. The channel, by and large, needs an alignment between the transmitter and the receiver. So that is one important aspect. We can call that as a drawback. But as a security, it is not going to be diffused in so many other places. So it is a security positive. So that is one. Line of sight is required, or at least a good alignment between the transmitter and the receiver. In laser sources, it is even more critical, right? Whereas in white light, it is a little less critical. Another issue is this ambient light and interference from other light sources. So basically, if I use one LED bulb for transmitting information, there will be other LED bulbs around the vicinity, and there could be a outdoor noise, which is the natural light, which can be interference sources. In addition to that, polished surfaces like mirrors, tiles, and roofs, ceilings, they can reflect, so they cause multipath dispersion. And last is we cannot have high mobility kind of applications. We can primarily look at low mobility. So that is a very high level description of the pros and cons. So I will quickly go through what you have to look for as so-called specifications for LEDs and photodiodes. The picture I have taken from the internet shows a smart bulb. When I say smart bulb, it's a bulb, but it's also having the middle bulge, having the electronics for converting information to light, as well as light falling on it as information. So this is essentially due to I will not read through the whole thing, but the gist is the following. If I use an LED as a transmitter, what is the equivalent to the transmit power of a RF power amplifier? We say an RF power amplifier is 20 watts, 5 watts, 2 watts. A Wi-Fi transmitter has quarter watts of transmitter, right? So what is that equivalent? That equivalent is called what is luminous flux. And that luminous flux unit is lumens. And if you go and see the LED specification in the street, you will have 90 lumens, 120 lumens, 160 lumens, and so on. And more importantly, they may not look at, specify lumens explicitly, but signaling rates are very fast, I, being a slow device, I will not recognize that. So that is a good thing, because signaling rates are much higher than 200 hertz, and standard takes special care of that to avoid flicker. And we can use this switching on and on to control the dimming aspect of the LED to increase the brightness or reduce the brightness, which is an artifact required for lighting, right? So there are techniques to do that by increasing additional symbols and intensity being changed, or the duty cycle of the switching waveform being changed. So you can change the dimming based on several approaches, and standards use certain approaches like time domain for on-off keying. And this is the picture I just want to show, that you can control the duty cycle, change the so-called DC level, and embed in between symbols if you want to increase the on time, if you want to increase the power, increase the 1 period, and if you want to increase the 0 period, and so on. So these are flicker and dimming are important things in LED. And in the receiver side, if you come, something similar you have to look for, and the main thing that you have to look for is, first of all, conversion of optical watts to electrical amperes, and that is responsivity, right? At the transmitter side, it was electrical watts converted to optical watts, the electrical amperes converted to optical watts. Here it's optical watts as input, but what is the electrical amperes as output? The responsivity is the so-called specification. Again, rise time is crucial. Now there are two devices here. Both are diodes. Both have junction capacitances. Depending upon the junction capacitances, you have rise times and fall times. And rise times and fall times will decide the modulation bandwidth. And receiver is very crucial. If you have a very fast switching LED but a very sluggish photodiode, you are not going to see the signal through. So photodiode is very crucial. Both should be having good or matching rise and fall times so that it becomes compatible. And field of view is another specification you have to look for in the photodiodes. It is to say that the rays entering into this cone will contribute to collection of optical energy for conversion to electrical energy. Okay, so this is a plot of responsivity. Typically, most of the photodiodes are geared for infrared. This is the infrared region, but we are talking about it can be used in the visible range as well. And another important thing that you have to do is, when you do the modulation as intensity modulation, the values, since it's optical power, right? It is optical power. The signal should be generated using positive alphabet signals, and they also should be real valued. So key takeaway in visible light communication is, compared to RFC, RF communications, you can use complex valued alphabet like QAM alphabet, and it will be also taking positive or negative value in the real and imaginary axis. But here we have to restrict our signaling values to positive and real. So that is a requirement, because we are radiating optical power directly through intensity modulation. So this is something which you will see as the channel, VLC channel impulse response. So you can see that if I transmit from one LED to a photodiode and then look at the channel impulse response, most of the powers is in the line of sight. About 50% of the power is in the line of sight. Zero, first path. If this is one bounce, two hop, which is one bounce, it reflects from a wall and then comes. So that contributes typically around 20%. So more than 70% of the power is from the line of sight path, as well as the bounce path from the walls. And multiple reflections from floors, ceilings all contribute, but they contribute to some about 20%. So when we talk about communication, we primarily are happy with a strong line of sight and maybe some reflections in the first bounce. And this H, what I talked about is direct line of sight, is given by this expression. This is a geometry. I have now defined this LED. It's a radiation pattern defined by the half-power semi-angle and the luminous flux that you choose, and the photodiodes, which is going to be determined by is field of view and sensitivity, which is responsivity, distance between these two, angles of interest, and so on. This is the expression. So it is to be noted that in VLC, unlike in RF, channel gains are static. And you can see this A by R square. A is the photodiode's area. More the area, better is the received gain. And R square is the distance. So this is something to keep it in mind, that channel gains are deterministic. Okay. So now I will keep away this MIMO. There are MIMO techniques one can use. Standards to some extent follow that. And this is a typical scenario that one can think of. In the ceiling, you have light fixtures, and you are working on a table, and on that you have a device, and that device can be communicating through these LEDs. Is a typical scenario in indoor wireless applications. And once you have MIMO, the key thing in MIMO is if you keep the LEDs a little close, depending upon the distance between the LEDs, the channels can show high correlation. So in VLC, channels are deterministic. Number one, they are not random. Second, if there are multiple LEDs and use that as a MIMO configuration, the MIMO VLC channel is going to have high spatial correlation, and you may have to do something special to handle that scenario. And modulation scheme for VLC, as I can see here, on-off keying, pulse position modulation, pulse width modulation, and there are several other modulation schemes. We will just keep it aside for a later discussion. People can go and figure out, but the standard talks about primarily these three modulation techniques, and all the three are essentially positive alphabets with real values, right, which are compatible with VLC. Okay, so now OFDM I will skip because that is more into research and some experimental building of the system, but I will go to something which is closer to what you may be interested in, what is going on in the standards world, in practical world, in the next 10 minutes, right? So standard 802.15.7, it is a standard which is meant for short range optical wireless communications, right? Let me quickly go through what it talks about. Okay, first of all, this standard is not very recently done. It has been done way back in 2011. It's about a decade since this first version of this standard was done. And very recently it was revised, and that revised version happened in 2018. And the key thing about this standard is it defines both the physical layer as well as MAC layer, just like any other local area network definition of the standard. This standard also defines the physical layer as well as the MAC layer. Another point which we have to recognize is this standard specifies for 5 components for both indoor as well as outdoor. When I say outdoor, for vehicular kind of applications. So it has both. So you have to recognize that there is no separate VLC standard for outdoor, but one of the 5 types is meant for outdoor. I will talk about its physical layer attributes in the next slide. Okay, and it defines 6 different physical layer types, 5 types, phi 1 to phi 6. Okay, and as I mentioned that flicker is an important eye safety measure, because if you notice flickers, it may create eye problems, particularly migraines and other things can be triggered. So the design of the waveform should be in such a way that flicker is not visible to you in normal eye, right? So for that, 2 things are done in the standard. One is idle patterns, right, to fill in some patterns so that it will be switching on and off, and it will not create opportunity to have some more zeros and more ones, which will create that kind of flicker, right? RL code is run length limiting codes, which also are meant for avoiding flicker. The dimming support is another thing for reducing and increasing the power. If you want for lighting application, you can adjust the pulse width, or you can put some compensation symbols that I talked about in one slide. So this standard takes care of that, because without it, there may be again other considerations, and people may object from the safety point of view and other power saving point of view. So they are taken care. So another important thing is it supports a wide range of optical sources and detectors. That is why I spend time in LEDs and photodiodes, what you should look for, because ultimately when you buy an entire chip, it may be all there, but even before you make the chip, you have to figure out what is the specification to look for. So the standard allows for you to choose the right set of sources and detectors. And the frame itself at the physical layer is very simple: synchronization header, physical header, and data service data unit. That is SHR, PHR, and PS data U. And there may be some gap here before the next frame starts. If there is an idle, this idle pattern the standard defines for you to fill. If there's a short packet and if there is a gap in between, this idle pattern will be put in, that is to avoid inter-frame flicker from one frame to other frame if there is a big difference in the duty cycle and other things. So there is going to be a flicker. So that is to avoid this idle pattern is given. And these are the three things. I think if I can go through this slide, I think this is going to convey much of what 802.15.75 stands for. Okay, let's look at the first three layers and three types. First type is for outdoor usage. Okay, and what that means is I can use this as communication in vehicles, traffic lights, and street lamps. That is what we said it is the vehicular network environment. And here, the data rates that it supports, there are a bunch of data rates, and the minimum is 11.6 and the maximum is 266. And you can see this is relatively low because several talks would have said I will have gigabit per second. I will have multi-gigabit per second using light. Mind you, using white LEDs, you will not reach that kind of gigabit per second. It is all monochromatic sources like laser beams kind of links where you will have those kind of speeds. So make sure that the understanding, if I use a light bulb in my home, will I get gigabit per second? Doubtful, very much doubtful. As of today, the standards talks about only megabit per second up to 100 megabits per maximum. But here this is outdoor. Outdoor is a little more challenging. A street lamp is going to have a high power source because it has to illuminate a large space of area below that. So it is a high power source. When it is high power, the driver current should be much higher. When the driver current is very high in current, then the switching speeds with which you can operate them will be slow. So that puts a restriction on the optical clock to be around 200 kilohertz, right? Whereas in the physical indoor communication, it can be much faster. So this is what I said. This is the switching modulation frequency. In digital communication, we have some certain amount of signaling interval. 1 over this 400 kilohertz or 1 over 200 kilohertz is the signaling interval. Inside that, you use on-off keying or variable pulse position modulation. Right? Very simple, using pulse width or pulse position and on-off keying, use this. So when I say that, look at the standard and then say 400 kilohertz optical clock, choose the corresponding devices in terms of both the LED as well as the photodiode. And because the outdoor environment is harsh, this standard specified outer Ritz-Salmon code and the inner convolutional code. It is a very heavy duty error control unit, but it is used. And RLL is used for mitigating the intra-frame flicker. So this is the outdoor scenario specification 5.1. 5.2 is, you can see this rate goes from 1.25 to 96 megabit per second. And your signaling bandwidth can be going up to 120 megahertz. So when I say 120 megahertz, if I have to say a compliant implementation of 5.2, my LEDs and my photodiode should be having switching speeds which will have signaling bandwidths in excess of 120 at least. Right? I cannot use a device which I chose for 400 kilohertz of optical clock to be used for a 5.2. I have to use a different set of devices to pick. And again, on-off keying with the FEC, no concatenating because this is indoor, a little less harsh. So use on-off keying and RLL for flicker control. And this is 5.2. And 1 and 2 are the key ones if at all it has to become very popular in practical world. Right? 5.3 is for using color LEDs. You can use multicolors, green, yellow, and blue LEDs. And then you can mix them in certain way and still achieve up to 96 megabit per second, and you can have up to 24 megahertz of optical clock. Okay, so the primary thing could be 1 and 2, 1 for outdoor and 2 for 5. And 2018 has introduced cameras or image sensors as one of the element in the whole game rather than simple photodiodes. So cameras is one element they are bringing in. This 5.4, 5.6 and 5 all are new elements compared to 2011 version. So 2011 had only 3, now we have 6. So I will not go into the details, but they are driven to have a lot of non-conventional light sources like video displays can be used, and cameras as receivers and so on, and different modulation schemes. And as a topology for the MAC, star topology is one, peer-to-peer topology is another, and broadcasting is another. Okay, so this is one standards compliant implementation that I saw in the literature. It's way back in 2014, so not that recent, but it makes the point. Creating this link is standard. Everybody will do, right? Many people will do. Take a light source, take a photo sensor, and radiate through some distance of certain meters, and you achieve certain rate. People will do that. Okay, so that I think is even a BTech level project or even a high school project may be done these days, right? But the point is how to engineer it in a way that is going to be suitable for an application, and that too to be a standards compliant one. And this paper talks about standards compliant one using COTS devices, commercially off-the-shelf items, and implementing all the modes of physical layer 1. So that is for outdoor kind of scenario. So they have tested for chat applications 4 meter range and video transfer 1.5 meter range. The interesting thing is they have used SDRs. This is an SDR platform. I think everybody does that now. This is an SDR platform, and use this data source, implement all the MAC layer and above up to bits generation. And once you have the bits generation, then you put it through this. I think SDR does much of the standards 5-layer implementation, and MAC may be here, and the real transmission happens here. And you can see this. This receiver is quite expensive. Right now, I think one of the key things is we think that LED cost is very low, photodiode cost is very low, but then I think we still are in a regime where it is a very tightly packed kind of thing, and you have to spend a lot of dollars or rupees to get the thing. So this is one example of implementation, and such implementation you should be available for the product developers. These are university kind of prototypes, but I don't know whether they are immediately purchasable kind of chips people can take and then implement it and then use it for an application. And I think we are having some more distance to go there. And this is for automotive application, and this is to say that we have outdoor applications which are very important, and the driver is intelligent transportation systems. So we have autonomous vehicles and a lot of things happening in the transportation. And in that thing, transportation safety is very important. And there VLC can play a big role, road safety, transportation safety, to make vehicle to vehicle, vehicle to infrastructure, infrastructure to vehicle communications. And again, use headlights in cars, street lights, and traffic lights. This is a picturization of what can happen. A car which is going front and the car which is going behind, they can communicate using a short range communication, VLC communication, to basically tell where I am, which is a GPS data, which is available, but I can tell what my GPS position is, and the state, what is my velocity, what is my acceleration, what is my direction of my travel. So that you can give this to the neighbors before, ahead of you or behind you or side and so on, using LEDs. And that is one of the driver in the road safety thing. In the RF, there is a technology which is 802.11p for the same purpose, which is called DSRC. But the problem with this DSRC is if a lot of cars are there in the road, density of the traffic is high, and everybody tries to use this RF. And this is based on Wi-Fi 11A, and you have a MAC protocol which is CSMA, and it is going to have a lot of collisions. So there is a technology in RF for this kind of road safety which is being proposed, 11p, but it has issues like packet collisions in high traffic densities. So VLC is a good thing for that in high traffic density conditions. So as you can see that you can send through the street lamps and maybe the so-called traffic lights and between vehicles, head and tail lights. And this is the last but one slide or so I will show. This is a joint 5G Vlc experiment done by some group in Italy, funded by some government and industry sources, which is talking about a joint use of 5G and VLC networks to provide real-time road information to cars. So this is what we talked about as a potential possibility This is a real hardware implementation and a field experimentation that is reported very recently as 2020. I think more such activities are expected, and even our own efforts maybe should be gearing towards, after establishing the basic things that can happen in a communication way, we have to look for the application side of things. So these people have, what they have done is, they have, look at this picture. This picture is what they have done. This is the infrastructure side, and this is a 5G base station, let's say. This is a 5G base station. This is a traffic light, and this is a car. These are the key elements. A base station, which is 5G base station, and there is a traffic light, and there's a car. The communication happens from some place where you generate some sensitive data for road safety. Let's say this is implemented by them using a combination of a Raspberry Pi and 5G modem. And this 5G modem talks to this 5G base station. But what this Raspberry Pi is emulating is collecting the IoT data or sensor data which are of interest to be conveyed to the road vehicles. Okay, so this sensed data is passed on to the 5G modem, and 5G modem through the air connects the 5G base station, and 5G base station in turn talks to another 5G modem, and that is going to be controlled by a Raspberry Pi 2 in this implementation, and that is part of this traffic light. This 5G modem is in this. This is data generating place, base station, and this is part of this traffic light. And once you receive it through the 5G modem, put it through VLC, right? This is the VLC. There is a 5G to VLC transfer, and that goes and gets to the car. And car has its photo receiver and the Raspberry Pi to do, and then give you a display of the road safety information, right? Now the question you may have is, 5G is there here in the pole signaling light. It may be in the car also. Why don't you use that? Okay, this is a simple question I will answer and then leave it, because you can yourself clearly see the reason also. There is a 5G place. There is a place where 5G modem collects sensed data for road safety. It is sending to the base station, and base station can directly send it to a 5G modem in a car. Why do you go through a light and traffic light sends it to you? Why not directly go from here to here? That is a question, right? You can see that again, as in the previous slide, I show that collisions can happen in the so-called high traffic density region, and you will end up with more collisions and more latency. I will show one last slide, which is the latency slide. And that latency can be avoided if there are more guys, and more importantly, some traffic data traffic can be offloaded to VLC. Why do you do all the work yourself and then burden yourself with collisions and end-to-end delay accumulation? Some of them you can offload to this, and safely this will send it to this. So that is the idea. High traffic density, RF will be crowded, RF interference will be more, and all these issues will be there. So VLC is a natural choice, and VLC will be offloading some of the traffic that you may accrue in the RF world. So this they have demonstrated in practical measurements. So they tested the following. They field tested the end-to-end latency in an integrated 5G VLC environment, and basically infrastructure to vehicle measurement campaign using a VLC-based traffic light. Right? This is the picture that you can see here, and this is the last slide. So you can see this thing. This is a snapshot of 3 Raspberry Pis CRO outputs. This is the Raspberry Pi 1, which is the IoT, which is the source, is generating some data. Some sense data is generated, and this is transmitted to the so-called base station. And this whole time it takes this box is to reach the modem in the traffic light. So it takes the longest, till about 9.5 milliseconds, 5G link delay. This is the 5G link, then there is some processing, and this is the VLC link, right? There are 2 links, and the end-to-end delay, one snapshot is generate some data, transmit it, and receive it at the traffic light, and then send it to the car and process that. So this is the VLC, the 5G link latency. This is the VLC link latency. So totally about 12 millisecond, and it is about 9.5 millisecond due to only 5G in this example. So they have collected a lot of data, plotted the histogram and fitted some T distribution for the end-to-end delay, And the idea is, it illustrated one possibility of using in practice 5G and VLC combination to work for you in road safety. This is an illustrative example. And in conclusion, I would say that visible light communication is a complementary technology to short range RF communication, and several hard to resist advantages. I would say hard to resist means initially what I told, oh, this is too good for leaving, so we should keep it. So, but there are matching challenges. When I say low matching challenges, we have to reduce the cost, you have to make it in good form factor, and you have to test it out in various use cases. There are several challenges to make that in a commercial way to be very possible. So there are challenges, but very hard to resist advantages compared to RF. But important thing is VLC need not be viewed as substitute technology for Wi-Fi and other RF. So VLC is nowhere as a substitute for any technology. Wi-Fi has its own strength. RF, they have their own strengths. Both VLC and RFC have their own strengths, which are complementary. So that is how I would like to see. So both will coexist and both may interoperate, but I think it's not one is not the substitute for the other. But more importantly, for the faster adoption of the technology and deployment, I think some new or not necessarily new, some niche applications should emerge, which will accelerate the adoption and deployment of the VLC technology. So with that, I will close my presentation and thank you for your attention. So I have finished at around 10:56. I will stop now and then take questions if there are any time.
Okay, thank you, Professor Chokkalinga, for the interesting talk. There are few questions which are posted in the chat, and if there are specific questions, if you would like to raise your hand and ask, you can. The audience can also do that. So let me start with the chat questions. So there's one question on what is the typical switching frequency of LED?
Okay, if I buy one LED from my main street in Sanjay Nagar, it will be around tens of nanoseconds. Okay, tens of nanoseconds means it's about a few megahertz.
Okay. The next question: what happens if the user moves in the indoor environment? What happens to the communication link?
Yeah, I think this is a issue. That's why I said cons. Pros and cons. We can support primarily no mobility, which is fine. I'm sitting and talking right now, and if I have my light in front of me or above me, it's not a mobility scenario. If I move around my home, if my light is close to me and so on, that's also okay. In airports and other things we can think. Only when the mobility is a little fast, it becomes an issue. So the use cases are primarily have to be thought out. So it is not a panacea for everything. You cannot drive at very high speeds and then say in a Doppler channel it will work. No. So it is for low mobility, but even between one lighting source to the next lighting source, if you walk, there should be a possibility for you to switch from one LED source to the next LED source. That are handovers, which are called auto cells. Much smaller cells, like we have femto cells in RF, but the auto cells, TTO, is the name given to VLC cells. But they are networking kind of issues, but they are in the research domain, they have been published, but in practice, we have to see how it develops. Mobility is an issue, but I think use cases are plenty in the no or low mobility scenarios.
Okay, fine. Is there a possibility of Li-Fi, Wi-Fi to coexist so that the person, if the user moves to from indoor to outdoor, they can have seamless transfer?
I think yes, and you will. The future phones may come with LED transmission capabilities, is what I believe, because right now you have an LED in your phone as a torch. And that can be used as a device for your communication. And when you are moving, you may use RF. When you are not moving, and you may, just like Bluetooth right now you're using, Li-Fi also may be used. And use case has to come about, and that proliferation has to happen. Both will coexist, and Li-Fi will have its space. We have to wait and see how it develops.
Will the repeaters increase delay in communication?
Yeah, I think they're talking about the optical repeaters. Any repeater will add delay. Yes, that is a standard answer. Any repeater will add delays, but it also gives, in some cases, the handover possibility or range extension possibility and so on. But time critical applications, you want us to see what is the latency that is required. So whether relaying is possible, or you have to work with only non-relaying scenarios and so on.
And for the vehicular application on roads, can VLC complement for certain offloading broadcast data kind of application?
Broadcast kind, see, rates can go up to several megabit per second, if not gigabit per second, right? So I don't know, because I think right now the focus is on near field kind of communication. Still, when you come close to street lamps, illumination, or the traffic lights line of sight, or the head tail, line of sight is what we are talking about. But when you are driving, when you want to have a large data transfer, video and so on, 5G is there, or even 6G will come. So there, I don't know. Indoor, I can see very clearly a big file upload, download that can happen due to VLC. In applications like vehicular, I'm not sure. Maybe.
And there's a question, is there any testbed or experimental work at IISc? So maybe I will take that question and mention that the last two talks are given by PhD students who are working on the VLC testbed at IISc. So you can hear more about our work in the last two talks. Right? Another question is, will VLC have a separate antenna source for radiation?
No. LED is the transmitter. LED is the transmitter. There is no antenna. Everything is embedded inside the LED itself. So there is no antenna per se, as in the case of RF. In fact, there may be mechanical designs inside the LED bulb or LED enclosures, which will make sure that phi half or half power semi-angle is this and so on. But they are all part of the manufacturing process itself. And there is no need for us to do any design in the LED. We may have to choose the right LED with the right specification and power rating, as well as the signaling modulation bandwidth and the radiation pattern.
Okay, fine. And then another question, how does the free space path loss of VLC compare with sub-6 gigahertz frequency?
Sub-6 gigahertz has frequency dependence inversely related to 1 by f square. So here we are talking about only the light intensity, so there is no frequency dependence here, but distance dependence in both so-called sub-6 gigahertz and VLC are 1 by d square. D is the distance, 1 by d square, both will fall. But I think microwave or sub-6 gigahertz, they have a much higher range. Means path losses are probably relatively less compared to VLC.
Okay. Apart from road safety application, is there any specific field of work going on currently?
In terms of indoor, see, there is a standard. Okay, there are people who feel that the standard has given a lot of weight to the payload in the transmission. Okay, so people have looked at their own proprietary modulation, proprietary MAC protocol, proprietary error correction or error control. So I think this standard may evolve more like Bluetooth once. See, once when Bluetooth came into existence a while back, people thought it is going to replace or challenge Wi-Fi. Wi-Fi was at that time 11B or graduating to 11A. At that time, Bluetooth came. Bluetooth 1 Mbps was talked about as big, and it was having TDMA, and it was having scatternet, kind of topologies. So it was thought that Bluetooth will challenge Wi-Fi, and Wi-Fi will win, and Bluetooth will be nowhere. And Bluetooth was nowhere for quite some time. But eventually, without much fuss, it came and sat in all our small, tiny devices. And that was a success for Bluetooth. So VLC has something similar in character. It needs the user application to define themselves and grow. Whereas Wi-Fi needs some standardization, big company development, pushing, marketing, this and that. Bluetooth did not probably have such a thing. Initially, there was a standard. After that, it proliferated on its own. We have our own headphones using Bluetooth, cell phones having Bluetooth. Everything is Bluetooth enabled. But VLC has something similar in flavor, is what I think. So, like outdoor environment road safety application, it is left to the users to define the use case and then build the technology for it.
Okay. What are the cons in having more access points for VLC?
What are the
cons?
Oh, yeah. Okay. So there are, strictly speaking, there are no cons in my opinion, because lights are there everywhere. You are not going to create a infrastructure for this specially. If there is a street in Margosa Road, you walk, all the street lamps are LED lights, right? So why are you worried about creating a new infrastructure to that? It is already there for lighting purposes. You go and sit in MP20 or Golden Jubilee, lights are there already. In my own office, I have recently installed 4 LED bulbs from my tube lights. So they are there. So they are access points. Every LED bulb or a combination of bulbs are access points. So you don't have to create new infrastructure. So cost-wise, there is benefit to that. But again, the issues are mobility, handover, they are issues. But access points, more you have, there is no issue. They will not interfere with each other in some sense, because you can always have techniques to isolate one from the other.
And if LEDs are used with, there be interference while doing communication?
You can use, as I said, frequency division multiplexing is what the standard calls. It's a misnomer. So phi type 1, phi type 2, right? Phi type 2, although I said that you can go up to 1.2 megahertz or so in the switching speed, right? There are other than 1.25 megahertz of switching speed, like 400, 600, and so on. So you can use 2 adjacent guys to use 2 different switching speeds, so that they will not interfere. So the capability is there in the standard. If I say that I have used a Phi 2 compliant device as my LEDs, I can use one LED to use one particular signaling bandwidth. The next I can use a different signaling bandwidth, and they will not interfere with each other in terms of their switching speeds being different, and they will be isolated in the frequency domain of the signal.
Okay, good. I think that's all the questions we have. So I would like to thank Professor Chokkalingam once more for the interesting talk and answering all the audience questions. So thank you very much, Professor Chokkalingam.
Yeah, thank you, Warren, for having me. Thank you all.
Thank you.
Bye.
So thank you. So next we move on to the second technical talk. This is given by Professor Abhishek Dikshit. He is a faculty in the Electrical Engineering Department at IIT Delhi. He is also affiliated with Bharati School of Telecommunication, which is a center in IIT Delhi. And he is one of the co-PIs in the 5G testbed project at IIT Delhi. And so he'll be talking about some of the work happening in visible light communication in his lab. And his broad areas of research interests include optical communication, optical networking, fiber-based communication, radio over fiber, and a lot other things, and also applications of those as well. Right. So with that introduction, let me hand over the controls to Professor Abhishek.
Thank you, Varun. Am I audible?
No, your slides are not visible, and actually your camera image is also not visible. Yeah.
Okay.
Yeah, now it's good. Now your camera is visible.
Yes. Are my slides visible now?
Correct. Yeah, it's visible.
Okay. Thank you, Varun, for having me to give this talk. I also thank other organizers from IISc. And I will also like to thank Professor Chokalingam for his previous talk, because that makes my life quite easy. A lot of things that I want to talk, he has already introduced them, so that would be easier for me. So this is the outline of my talk. First, I will like to introduce visible light communication, what it is. Then we will focus on multipath channel modeling, channel characterization of multipath VLC link, the modulation schemes used in VLC, multiplexing techniques used in VLC, and then I will give some demos for the work that is done at IIT Delhi. So, as it has already been told, what is VLC? It is a short-range optical wireless communication technology. And typically, the range of operation is between 400 terahertz to 800 terahertz. That's the visible range. It uses primarily LED lighting, but you can also use laser, for which I see Bangalore is working. So I will leave that to them. But we will focus in this talk on LED as a source in optical wireless communication technology. And why we use VLC is because it can provide both illumination and communication. Okay, so you can also have a look at this electromagnetic spectrum to understand this better. So visible light communication falls between 400 terahertz to 800 terahertz. So this is the basic block diagrammatic representation of VLC. So you have data from internet available. Then we feed this data to LED driver. This LED driver has other control like dimming control and biasing control. This LED driver drives an LED lamp which emits light. This light falls on photodetector, which converts this light into current, and this current is received by receiver, and based on the current that the receiver is getting, it gets back to the data. And this data can be fed to a PC or a computer, and you can access video applications or voice application on your PC. So this is basically the setup of visible light communication. This Professor Chokalingam has already talked about. So if we look at the luminance efficacy of various lighting devices, we see that we have made a lot of significant progress. LED currently has around 300 luminous per watt. So that is much higher compared to a fluorescent lamp and of course to other lighting infrastructure. And also the lifetime of the devices has increased. So if we look at the lifetime of an LED, it is about 100,000 hours, which is significantly much higher than other lighting sources. So one reason why we want to use visible light communication and why we want to use LEDs is because of these two things. So having a higher luminance efficiency means higher energy saving in the network, and having a good lifetime means that replacement cost and operational cost of the infrastructure is low. And if you look at this picture, what we can see from this picture is this brown color thing is LED. So as we are going from 2013 to 2021, the percentage of LEDs is increasing. This is the production of devices. So if we look at this slide, it is clear that as we will move forward, we will have more and more LEDs produced compared to other lighting sources. Okay, so these 2 points indicate to us clearly that LEDs will have a very good energy efficiency and it has a good reliability. And together, based on these two factors, what it would do is it will also lead to the production of more and more LEDs. LEDs will replace more conventional sources of light, and thus LED as a source in visible light communication is good. So this slide captures some of the advantages of LEDs over conventional lighting sources. As I have already mentioned, it is highly energy efficient, it generates less heat, it can reduce energy consumption by about 80%, it has a longer service lifetime, it has a higher luminance efficiency, It's free from hazardous substances like mercury. It has high modulation bandwidth. So it also depends upon the kind of LEDs you have, but in generally it has a good modulation bandwidth running into hundreds of megahertz. It's tolerant to humidity. It's smaller and compact in size. So all these advantages have been derived from this research paper, which I indicate the below of my slide. So looking at various kinds of LEDs that we have, this is phosphorus coated LED, PC LED. Then we have red, green, blue LEDs. Then we have micro LEDs, and then we have organic LEDs. Primarily for communication, people have been using phosphorus coated LEDs or red, green, blue LEDs. And if we look at the advantages of this phosphor coated LED, it's low in cost, it's low in complexity, it has a reasonably high efficacy, it has a smaller bandwidth compared to red, green, blue LEDs. Its bandwidth is around 3 to 5 megahertz. But if we are looking at low data rates like 10 Mbps or 20 Mbps, then we can use this phosphorus coated LED. And this is currently being used for illumination. And this is also referred, I think, in the previous slides as white LED. So I will also talk, or I will give you some hints as how can you increase the bandwidth of phosphor coated LED later in the slide. And this is being done by using a blue filter at the receiver. So the problem why the bandwidth of phosphor coated LED is low is because you know how it works. Its blue light is converted into yellow light because of this phosphor, and the time for this is very long. And if we can block all this yellow light, and if we just have blue light at the receiver, then the bandwidth can be increased. So if we use blue filter at the receiver, then the bandwidth of this communication system can be greatly increased to around 100 megahertz. So this is one idea that we are using in our own project, where we are getting a bandwidth of phosphor coated LED as around 25 megahertz, not 100 megahertz. 100 megahertz has been claimed in certain literature, but what we have been able to get is around 25 megahertz with a blue filter. So why VLC? I think this must be now clear to every one of you, because LEDs have a lot of inherent advantages compared to other lighting technologies, and there is a potential market growth for LED technology. And of course, this RF spectrum is getting over congested, and it can act as a supplement and substitute for this radio frequencies technology. Again, there are a lot of advantages which has been captured in the previous lecture. I just reiterate them. So we want to get rid of the spectrum crunch in RF spectrum. It has low electromagnetic interference. It's very secure because light cannot go out of your room. So whatever you talk in a room, it stays in a room. So it's secure in that sense. And because every room can use independent lightning communication, so we refer to that as spatial reuse. Even within a room, if one LED is transmitting a signal, and if there is another LED which is far off from the current LED, then there is no interference between the two LEDs. So we can make use of this idea, and we can increase the spatial reuse of our network infrastructure. It's safe. We have been exposed to light for a lot of years now already. Human race has been exposed to light for a long period, and we know that it is safe. It doesn't cause us cancer or deadly things like that. It's highly energy efficient, and of course we can integrate or implement this in a smart power grid and integrate lighting infrastructure as well. People claim this to be a low cost, but I don't think this as true at this moment. It is at this stage, making VLC communication link is expensive. But if we continue with the development, and if the progress happens in the area of VLC as is predicted nowadays, then we hope that in years to come this will become low cost technology. This slide I have taken from this paper, Wireless Infrared Communication. This is a very good slide I guess Professor Chukalangam has talked about intensity modulation and direct detection, which is primarily the modulation scheme that we used in visible light communication. So information is communicated in terms of the intensity of the light, hence the name intensity modulation. And this is directly received by a photodetector without any fancy things, and this is known as direct detection. So basically, this will be the mode of modulation schemes used in the VLC setup. So if we compare this intensity modulation direct detection system with radio, we see that in radio bandwidth is regulated. So we have to buy the spectrum from government and we have to pay for it. Visible range is free, so that is a good advantage for VLC communication. Approval is not required, and worldwide compatibility can be accrued in this. Radio passes through walls, whereas VLC signal doesn't pass through wall, and the advantage for that is we can have less coverage, but that also means that it is more easily secured and we can have independent links in different rooms, as I have already mentioned this. Multipath fading happens in radio, but in visible light communication, there is no multipath fading because the wavelengths are very short. The wavelengths are very short and the receiver area is comparatively larger than the wavelengths. Then, of course, you have diversity effect at the receiver and there is no multipath fading. And this leads to simple link design in VLC communication. There is multipath distortion both in radio and in VLC. Path loss is high in both of these technologies. Of course, intensity modulation, direct detection of VLC links are more immune to shadowing effect. So if you have an object between a transmitter and receiver that completely kills the signal, in radio is more tolerant to shadowing effects. There are no shadowing effects seen in radio. So other than that, path losses are high in both these technologies. Background noise is, or background light acts as a dominant form of noise in intensity modulation direct detection link, whereas the noise in radio is the signals of other users. As I've already mentioned that in intensity modulation direct detection, the input signal is intensity or power of the light, right? So if you have seen equation like yt equals to xt plus nt, xt in case of visible light communication is power, whereas xt in case of radio communication is amplitude. Okay, so that's one difference. Signal to noise ratio is proportional to mod of xt square dt integration in radio, and in intensity modulation it is again the same. This power is converted into current at the photodiode. And of course, the signal power is square of the current. So we have got this formulation there. The problem now because of these two things is, if we want to have the same signal to noise ratio at the receiver, and this input xt is the power in optical communication, if there are losses, let's say if there is a 10 dB loss in an optical channel, that will lead to 20 dB decrease in signal to noise ratio, right? So to maintain the same signal to noise ratio, the power transmitted in optical communication must be higher. So that is a disadvantage of visible light communication. It typically leads to higher transmitter power requirements. Okay. Average power is proportional to this in radio, and in intensity modulation this is this, because power is xt. So average power is this. What these two things will mean that we need to choose xt with high peak to average ratio. So that is good for visible light communication. So these are some typical differences between radio and visible light communication. Most important difference I think is that the information is transmitted in the form of power of the light, and that leads to some other differences like the transmitted power must be higher in visible light communication, and we need to choose a signal with a high peak to average ratio. So there are various applications of VLC. VLC can be used for indoor wireless communication, as we know. It can be used in RF interference sensitive places. It gives higher security. It's good for energy harvesting. It can be used for indoor positioning. It can be used in underwater communication, ad hoc networking, Wi-Fi data offloading, a lot of places. Okay. In this slide, primarily we will be focusing on the use of VLC for indoor wireless communication. So there are certain challenges also in visible light communication. For example, if we look at these two users, they are connected with these LEDs, but if they move off from this LED, then the connection will be lost, right? So there are a lot of issues in visible light communication because of this field of view misalignment. So basically, the receiver of visible light communication is very sensitive to its location. If you move the receiver even by a bit, then there is a very high probability that the signal will be lost. So that is one problem with visible light communication. Of course, because we want to use several access points, there can be some co-channel interference, and this can be blocked by any object between the transmitter and receiver. And this communication is primarily line of sight. It has a smaller coverage area. It has mobility issues. And we want to sleep sometimes with the light switched off or maybe 90% switched off. So we need to have a VLC system that supports dimming or reduction in the lightning that is available to us. Then it is also prone to flickering. So if you have long trains of ones and long trains of zeros, that is a very practical situation in any communication system. Suppose we are talking on telephones, we don't speak too much, and then there are long periods of silences. Long periods of silences means long trains of ones, and long trains of ones and long trains of zeros might reduce the frequency of your communication system, and you might see the light flicker, and we don't like to see that. And so we need to have modulation schemes that is immune to this flickering. And we also have to support a basic level of illumination, and this LED modulation bandwidth is limited. Though we claim that we have a lot of bandwidth in visible light communication and in optical communication, that's not true, because currently LED acts as a limitation in VLC networks. Okay, so these are typically the challenges in visible light communication. So in this, after understanding the basics of visible light communication, let us move to this multi-path channel modeling. So the slides are from our own research at IIT Delhi. So I would like to present the key results in this area. So I think all of this has been introduced by Professor Chokkalingam already. So let us imagine that we have LED source and we have a photodetector. LED source has a semi-angle. So semi-angle forms the cone in which LED transmits most of its light, and receiver also accepts the light in a cone, right? We can imagine this to be a cone, and the angle of this cone at the receiver is known as the field of view of the detector or receiver. If light doesn't fall in this cone for the receiver, then that receiver doesn't receive it. Okay, so now let us try to understand that what happens when the light rays is transmitted from LED. So we are using this ray model because it's easier to understand. So if the light from an LED falls directly on the receiver, this is known as line of sight path. And what might happen is also that the light may fall on the receiver, which is reflected from the wall. Okay, and so this path is known as non-line of sight path. And there is one reflection involved, as you can see in this slide. What might also happen is you can receive the light ray which is reflected twice, one from this wall and the second time from this wall. So there are two reflections involved here. So this is a non-line of sight path with two reflections. Okay, so in our work we consider it's not possible to consider maybe 10,000 reflections in the system, right? So we have to limit or choose the number of reflections that we may consider in our work. So most of the results are with 3 reflections. We have considered up to 3 reflections, and the rays which are received after, let's say, 4 reflections, of course, they will be reaching with very little power, so they will not be very significant and we can safely ignore them. right? So the number of reflection or reflection order that we consider is important. So now, after having understood this, we can also define the channel impulse. So the channel impulse response is between the ith source and jth receiver, right? And here we are just presenting the channel impulse response for line of sight path. This has already been talked in the previous slide. So it depends upon the gain concentrator. So we might be using some optics at the receiver. So gain concentrator comes from that optics. Then it depends upon the field of view of the receiver. It depends upon the LED semi-angle. It depends upon the area of the receiver. It depends upon the distance between your transmitter and the receiver, and so on and so forth. Of course, it also depends upon what is the Lambertian order of your LEDs and things like that. So this channel impulse response can be calculated between the source and receiver for line of sight path. We can also calculate the channel impulse response for non-line of sight path, assuming that we have K reflections. I will not explain this in more, but this can be very simply derived from this expression. So when we have K reflections, you have to assume this as a receiver. So for example, if we let us have to consider two reflections, then you can consider this as a receiver. You can calculate the channel impulse response between LED source and this point, and then you can consider this as a transmitter and this as a receiver. You can have the channel impulse response between this point, and so on and so forth. You can go and calculate this in an iterative fashion. So we have done all of this, and we can also calculate the channel impulse response provided there are more than one sources available, and the formulation for that can be given like this. It's harder to explain, but it's easier to see. If you stop for a while, think about this for 1 minute, this will be clear to you. So anyway, this channel impulse response, we have calculated it, and we have simulated this for certain scenarios. So the first scenario is what happens if we have a big room of 5 meter by 5 meter, and the standard height that we have considered is 3 meters. So what happens if we have a room of this dimension? What happens if we have a transmitter receiver separation of 2.15 meters? What happens if we have LED semi-angle of 60 degrees, though we will also vary the semi-angle in the results. And these are some other specifications that we have considered. The most important thing that we want to find out after calculating the channel impulse response is the delay spread, the mean value of delay spread, and root mean square value of delay spread. Because delay spread decides the coherence bandwidth of the channel. Coherence bandwidth is really important if you want to see what kind of data rate we can have over a particular channel, right? So delay spread, intuitively we can think of this as the spread in the impulse response of the channel, right? And there are various ways to calculate it. A lot of people have been using in the literature on wireless communication root mean squared delay spread, which is defined like this. It's a function of the channel impulse response, and so on and so forth, right? So let us see the results for this, and this is a scenario that we have 4 transmitters indicated by yellow color, and at all these purple boxes we can have a possible receiver. Okay, so this is the situation, and the dimension is 5 meters by 5 meters. So this is what we have got, and there is a little bit of surprise in these results. So what we are showing is root mean square delay spread, and we want to see this as a function of LED semi-angle, and these purple curves are with reflectivity 0.2, the green curves are with reflectivity 0.4, blue curves are with reflectivity 0.6, and the red curves are with reflectivity 0.8, right? Of course, as reflectivity increases, delay spread tends to increase because there are more non-line of sight paths that are available at the receiver with significant power. So of course reflectivity will not be as high as 0.8, but we want to characterize this channel for the worst case situation, right? Most of the communication systems are designed for the worst case thing. So we also want to see what is the worst case for this VLC channel. So and also we have purple, green, blue, and red color curves for different number of reflectivity that we have considered. So we have considered 1 reflectivity, 2 reflectivity, and 3 reflectivity. If we consider this purple curve, then we see that this doesn't change much with the number of reflectivities that we can consider. Of course, there is some difference in this red curve, but not that much. So if we consider more than 3 reflections, then of course the effect is negligible, and thus we haven't considered more than 3 reflections for these curves, right? So what is a surprise in this curve is, as the LED semi-angle increases, what is expected as number of non-line of sight paths will increase, and as number of non-line of sight paths increase, the delay spread tends to increase. So this is okay, but we see that there is an optimum point, and this optimum angle is somewhere between 10 degree to 15 degree. And why do we get this optimum angle is because, for example, if we have the semi-angle as 5 degree, what happens? There is no not even line of sight path between a transmitter and receiver, because now the LEDs are quite directional. So directional that a receiver is not receiving anything from line of sight path as well. And the only signal that it will get is from non-line of sight path, which might be reflected from here and there. And finally, the signal that it will get will be having a lot of delay spread. Okay, so the signal power when the LED semi-angle is very reduced, let's say 5 degree, will definitely decrease, and most of the power that we will get at the receiver is from the reflections, and so it will have significantly high delay spread. This is what we get in the simulations. And this delay spread reduces as you increase the LED semi-angle, which is expected because then the number of line of sight paths begins to increase. And if you further increase it, then the number of non-line of sight paths again increases, and so there is an optimum somewhere between 10 to 15 degree. So what we learn from this slide is we should have LED semi-angle somewhere around 10 to 15 degree. That is optimum to reduce the delay spread. Delay spread can also translate to coherence bandwidth. And so what kind of coherence bandwidth do we get in our system? So if we choose an LED semi-angle between 10 to 15 degree, we easily get a coherence bandwidth of 30 gigahertz, worst case, right? So we have to look at worst case situation. So this is not bad, right? Because LED modulation bandwidth is much smaller than 30 gigahertz. So of course, whatever you will be transmitting can easily be received by the receiver without any problems from the channel. So we do not have to worry about the channel as such. It's nice, it's good. It has a good coherence bandwidth. And these are some other curves. So this delay spread also depends upon the location of the receiver, where the receiver is. So we just want to show that it's a function of that, and coherence bandwidth is also a function of that. So we have shown it in these two curves. Now we have already talked about this. Based on the location of the receiver, you can have a maximum, average, and minimum value of the delay spread, right? You may have some places where the delay spread is very minimum, right? If you're directly beneath an LED, and if you are at the corner of a room, your delay spread may be higher. So you can have a maximum value, average value, and a minimum value. We can go with this maximum value of delay spread because again we are designing the system for the worst case, and we can do the similar exercise for coherence bandwidth, and we can look at what is the minimum value of coherence bandwidth, and if we have the right orders of LED semi-angle, then minimum coherence bandwidth is good. You can have a coherence bandwidth easily of 1 gigahertz for a worst case situation, which is good. It's not bad, right?
It looks like there is some technical issues and Professor Abhishek got logged off. I think he'll wait for a few minutes. I think he will reconnect. So sorry about that. I think we'll wait for another 2-3 minutes. If he still has some technical issues, then maybe we can go along with the other presentations and then come back to Abhishek's presentation subsequently. So please be patient for a few more minutes. Okay, I think in the interest of time, we can probably move on to the next talk, and we will try to connect with Professor Abhishek offline and get him to connect to Teams shortly. Right. So, so the next talk, the next two talks will be given by the people in IISc who do the actual work. So these are the talks by two PhD students who are working on the VLC testbed at IISc. So the first talk will focus more on the optical system level implementation of the testbed. The second talk will be on more on the overall system level implementation. So the first talk will be given by Mr. Fahim Ahmed, who is a PhD student in the EC department at IISc. So with that introduction, Fahim, can you share your slides?
Hello? Yes, sir.
Yeah, please go.
Sorry. Is it visible, sir?
Yes, it's visible, but yeah, it's not in slideshow.
Yes, sir. Yes, I'll put it.
Yeah.
So,
Okay. Go ahead. Yeah.
so thank you, sir, and thank you for the to the organizers to give this opportunity to share our work, what we are doing in our lab at IISc with the people. So I will be giving my talk, which is based on the for the laser-based visible light communication hardware system design. And the previous two talks was very good and given the some detailed analysis about the LED implementation in visible light communication. And the another talk was by the Professor Dikshit from the IIT Delhi. He was giving very good analysis of this multipath reflection and all for the coherence bandwidth and the delay. So I'll be covering this topic, and the most of my talk will depend on the laser-based implementation, lab level hardware system implementation. So first of all, I will be giving some hardware design system, what components are required, and then the D65 illuminant, what is D65 illuminant, and what will be the and what is the maximum permeable exposure limit, and the LED based and laser based implementation. Then I will be switching to the work what we are doing in IISc, and mainly we are focusing the optical system design to increase the link length and to increase the throughput of this system, and then the future opportunities. So first of all, I will give a quick overview about the setup, what we can use in a generic way. So this is the setup for the visible light communication. This is the transmitter, this is the receiver, and in transmitter what we have the first of all we need to have the light source. It can be LED or laser diode with mount, and the next is the phosphor, which down converts the light, blue light into the white spectrum, or we can use the diffuser also here if we don't want to convert the color of the light. Then the transmitter lens, just to direct the light in a particular direction to focus in a narrow region, in narrow area on the receiver side. Then on the receiver side we are having a receiver lens just to concentrate the light on a small area detector, and detector can be the pin or APD photodiode. So next is some hardware components what we use for the lab level implementation. The AWG we use, and then we use the phosphor just to down convert or just to change the color of the light to make the source illuminable, and then the lens we use to focus the light or to concentrate the light on the receiver, and then we use the optical filters also if we want to discard some wavelengths on the detector. Then we use the detector to convert the optical signal into electrical signal, and for data analysis we use DSO, and to control to operate the laser diode at fixed temperature we need this current driver operator, current controller, and the temperature controller. So what kind of light sources we can use, like the LED, laser, or superluminescence diodes we can use. But LED, as they talked in the previous two talks, we came up with it has the low bandwidth, modulation bandwidth, but it is good for illumination. So depending on the application, we switch to the laser diode or switch to the superluminance diode. Laser diode has the bandwidth, very high bandwidth, tens of gigahertz. So for high speed communication, we can use this, and it gives the power in hundreds of milliwatts. So for high speed, for over a long distance communication, we can use this laser diode. And the another is the superluminance diode. For superluminance diode shows the property of both, like LED, of LED and the laser. So with low coherence, it gives the low coherence nature of the light. It gives the high power and the moderate modulation bandwidth. So in some region like in Japan, we cannot use the laser diode. So the government of Japan are not allowing to implement the laser diode based VLC commercial products. So they have to use the superluminance diode that has the low coherence light. So that's why people are now switching to the use of the superluminance diode in VLC. So another thing another thing is the CIE standard D65 illuminant. we are talking about the visible light communication and we are talking about the illumination. So we should come to know like what kind of color shall we have from the transmitter, from the LED, what we are using for the communication. So color of the light is represented by this gamut. This is the D65. And what is D65? D65 standard is of the standard of International Commission of Illumination, and it is the average day midday light. So around 12 am, what the color of the sunlight is, that is called the D65. And the CCT is the like correlated color temperature. What is the temperature of that correlated color temperature of the D65? That is 6500 Kelvin. And the CRI is 100. So what is CRI? CRI is the color rendering index. It tells about if we are illuminating an object and we are using a source, so how the color of the object will look like, whether we are able to see the exact color of the object or it is hampering by the color of the light source. So it is whether it is changing or not. So that is given by the, like, we can check for with the CRI what kind of color is there. And this is the spectrum of the D65 illuminant. So we can see here near ultraviolet light, the spectrum intensity is going down very rapidly. So this is the spectrum for that. So this was all about the D65 illuminant. So next we came up with, like, if we are using a laser and if we are using a LED, whatever, then what can be the maximum power we can have, so that we will not be so that it cannot damage the eye retina or it will not be harmful for the human being. So this is about the this is the standard, American National Standard Institute. So they have talked about this, and this is the graph for the different wavelength spectrum and the as a function of the exposure time. So let's say for maximum exposure time, the 1000 seconds, how much power should be there? So the maximum, the MP level should not exceed for the 0 dB, beyond the 0 dBm per centimeter square for this wavelength range, 400 to 700 nanometer. So if it will exceed from this range, it can be harmful for the human eyes. So that we need to take care of that. And the next, I will be switching to the LED based implementation, the MIMO implementation. So in this in this technique, what the transmitter, like we are using, they use the 4 transmitter, separate transmitter, LED 1, LED 2, LED 3, and LED 4. They are using the NIR LEDs, and the separate transmitter lens are also there. So and we are getting the image of this on the receiver PCB. So we are using a single lens here, right? So they are getting the image of this transmitter on this PCB. So this is a kind of imaging receiver, and they they fabricated these photodiodes 2x2 on chip well in a low cost CMOS compatible process. So the bandwidth is very limited. So they to increase the bandwidth or the frequency response of the receiver, they used a second order LCR equalization circuit also. So the aggregate data rate they have achieved 600 Mbps over a link length of 1 meter. So next I will be switching to the laser diode based implementation. So for laser diode based implementation, we need to use a diffuser, because if we are using the blue laser diode, we need to convert the light into the white spectrum, so that the same transmitter we can use for the illumination and communication. So this technique mainly focuses on this illumination part. So they used a yellow phosphor. After getting this, after the blue, it down converts the blue color of the light into the white spectrum, and at 0 degree angle what is the color of the light, and at 60 degree what is the color of light. So they have done the detailed analysis of the illumination in an angular direction also. So this is more close to the D65. So D65 illuminant is a like reference point. If someone is trying to make a transmitter for Li-Fi, so what should be the color of the light? So they tried to achieve this, the D65 illuminant, and they are very close to that. And the data rate they have achieved for the different lux level at different link length, This is like 8.79 Gbps by using the 32 qm OFDM, and the maximum data rate they have achieved is 10.09 Gbps with the bit loading and power loading by using 2 channel. And this technique, in this technique, they used the imaging receiver also for the 2 channel, 2 separate channels, transmitter, 2 separate transmitter, and the image of those transmitter we are getting on the receiver. So next is the visible light laser diode based VLC system compatible with the lighting fixture. Let's say we are having a light source that is used only for, that can be used only for communication. So if we are having the NIR laser, that is not good source for the communication. So that can be used only for illumination. So in this technique, what they have done, they used only the NIR laser for the communication purpose, and they claimed like the lux level of this NIR laser is very small, is very less. So it cannot be, we cannot be differentiate between the what light is coming out from the tube light or from the LED in indoor in a room, or and where is the spot we are getting. So that's why it is the compatible with the lighting fixture, and they have done this. They have checked for the communication capacity also. So as they are changing the data rate, the BER is going is increasing with, and they use the on-off keying modulation. And over a link length of 12 meter, they have done this experiment, but they didn't talk about the eye safety issues, because if they are focusing the light in a very small spot, so maybe the intensity will go beyond the 0 dBm per centimeter square, that is defined by the American standard for the eye safety. So they didn't talk about this value about the eye safety issues. So next I will be switching to the because I have covered the topic when we will be using the laser diode, blue laser diode, and we need to use the yellow phosphor to down convert into the white light. So that is not the only option. The other techniques are also available to convert the blue or the NUV laser light into the white spectrum. So in this technique, they used the 3 phosphor, the RGB phosphor, and they implemented this to generate the white light, and how the white light color will change with the biasing current of the laser diode. This is representing the color of the light is changing with this biasing current. And why they use the NUV laser? Because if you will see the solar spectrum, so at NUV laser the intensity goes down very fast. So that's why. And if we will use this NUV laser, then the background noise will be very small. So that is the idea behind this work. And next, this is the some literature on the color converter, because I have covered the phosphor based, I have covered the RGB phosphor based, and the yellow phosphor based. So some other techniques are also available. So these are the literature for that. And the next is the optical system for the underwater communication. So what is the need of optical VLC, or we can say the visible light communication under in a water medium? So these are the some applications for that, like oceanography study, offshore oil exploration. And why we are switching to the visible light wavelength? Because we could use the acoustic wave, microwave, or RF we can say, but for the acoustic wave give the very slow response. I mean we cannot transmit at a very high speed, so communication speed will be very slow, but it can go over a long range. For the microwave, it is highly dependent on the water. See, attenuation is very high, so it cannot go over a long range communication. We cannot use it for that. And the data rate we can achieve the high speed with this RF signal, but it will not go over a long distance. And next is the blue LED, blue laser. We can use the blue laser, so it does attenuation is less, but we can communicate over a 10 meter, and this can be used for a high speed communication. So they in this technology they did the experiment attenuation, and they use a bathtub here, and they did for this, and the BER performance and the data rate they are showing in this. for our link length, how the BER is changing. And the next is the RGB based diffused and diverged white light generation. So we can use the red, green, blue laser diodes also to generate the white light. So in this technique, this is the we are combining these three. They are combining like these three beams to make one beam, and they are collimated. They are making the diameter of this beam almost 5 mm, and they are focusing on this light on a diffuser. So we can see here, without diffuser, like without a frosted glass, if we will be using a convex lens only, so how the color of the light will be distributed. So these are the colors we can distinguish. So it is not a good source of illumination. So to make it good source of illumination, we need to use a frosted glass. So they used a frosted glass here, and we can see here the color illumination is very good. Uniformity is very good. These are not distinguishable. Like we cannot distinguish this color is that, or the position of the colors. So these are very uniformly distributed here, and they checked for the communication performance also. They have done like 8.8 Gbps data rate performance with the 16 km OFDM over a link distance of 0.5 meter. These are some literature on the white light generation. So from different group across the globe, they are using the different techniques to combine the RGB laser or RGB red, green, blue with the ultraviolet or with the yellow color laser diode. So another thing is we have seen like what should be the color of light, what should be the MP level, the maximum intensity of the for the communication, and then we saw how can we convert the blue light into the white spectrum, and how can we generate the white light with the use of RGB, and why we are going to the RGB laser based implementation, because we want to use the WDM kind of technique to increase the data rate or channel performance. So that's why people think about according to the application. So next point is, if receiver is a mobile, then how we will steer the beam. So this is the technique they have used, the MEMS based technique. They are tilting the MEMS according to the steering, like where we want to steer the beam, and the steering range of this MEMS mirror is around 10 plus minus 10 degree. But what they have done, they used this magnification technique to increase this steering range. So by using this by using this convex lens of 50 mm diameter and 32 mm focal length, they have increased the steering range up to the 38 degree, plus minus 38 degree. So the magnification factor is 3.8 there. And this is the graph is showing about this, like if we are changing the steering angle, how the received power is changing, how the data rate is changing. So without any magnification system, it is very much flat. So why it is happening, because the diameter of the beam spot is not changing here without convex lens. But with convex lens, as we are changing the steering angle, the divergence is changing. That's why it is maximum at the center and it is going down on either side, on both the sides. So this is the communication performance they have checked. So this is this black dots is for the green light only with the Iasc, and this white dots with the white light for the Iasc. So they have achieved up to the 10.4 Gbps and 7.4 Gbps with green light and with white light respectively. So next is the
time check. You have 10 minutes left.
Okay. Okay, sir. So this is the kind of single input multiple output MIMO system, and in this, like they use the SLMs, special light modulator. Single beam is coming and they are generating the 9 spot in 3 cross 3 matrix, and they check the power uniformity, power uniform distribution over the these spots here. And next is the optical systems designed for the VLs. Like they use the techniques of the liquid lens implementation in the smart link, so that the for a variable link length. So there is a 53% improvement is there if you are using the liquid lens. So the path loss is change in the path loss is very small. If we are not using the liquid lens, it is very high. So they used this technique for that. And next is the what work we are doing in our lab at IISc. So I'll be explaining that. So this is the work what we are doing. We are mainly focusing on the optical system design for the transmitter and receiver, so that we can increase the link length with high speed data rate. So what we have done, the idea is that, like, this is the transmitter laser, then the phosphor, then the transmitter lens, and the receiver lens, and the photo detector. So if we will, this is like the path loss optimization for a particular link lens. Let's say, suppose the mobile user is a mobile, and we are close to somewhere at 25 centimeter. So we need to change the position of, if we will change the position of this transmitter lens from the phosphor and the detector position from the receiver lens, then we can optimize the path loss for that particular distance. Let's say we are at 300 centimeter, receiver is at 300 centimeter. So we need to change the position again of this. We need to change the distance between these two and these two. So this is the technique behind this, and we have done some simulation, and we opt for the we chose the two link length for the experiment, 25 centimeter and 300 centimeter. So for that, we are getting how the color of the spot will look like, and how the color of the spot are changing as we are moving away from the transmitter for the fixed transmitter and receiver lens position from the phosphor and the detector respectively, for these two optimized location, 25 centimeter and 300 centimeter. And this is the communication capacity. We checked for the communication capacity also. So for the 25 centimeter optimization, the BER is very less. As we are moving away from the transmitter, the BER is going high. So it is like a d square 1 divided by d square dependency of the path loss. So, but here for 300 centimeter optimization, the BER is very high as we are close to the transmitter, and as we are moving away from the transmitter, the BER is going to down. So we achieve the 1.5 Gbps data rate over a link length of 300 centimeter with this kind of optimization. So we try to increase the link length of the system in our lab. So next is let's say if mobile user will move transverse in the transverse direction of the propagation, then how to steer the beam of this kind of extended source. So this is a kind of extended source what we are using in the previous work also. So this is the laser, this is the phosphor, which is down converting the blue light into the white, and then the transmitter lens. But this time we fixed this transmitter lens position from the phosphor according to the 300 centimeter optimization. And we have fixed this transmitter lens on the linear stage, so that we can move this lens position in transverse direction. So let's say we are moving the transmitter lens in this direction. So how the beam will tilt? So these are the ray tracing diagram for 0 degree for 0 decenter, 0 mm decenter. How the rays will go towards the receiver lens, and for let's say 6.25 mm. So rays are tilting, and it will fall on a receiver lens at some angle. So this is a kind of beam steering with the solid lens, and we are decentering the transmitter lens position, and the maximum steering range we got from minus plus to 7.1 degree over a link length of 300 centimeter with the data rate of 1.5 Gbps. And why this? And we will, let's say if we are steering the beam, so how it will affect the collection efficiency, and why the collection efficiency will go reduced. So this is how the collection efficiency is going down with the steering range. And why it is going down? Because some coma kind of aberration on the detector is there. So this black circle is for the it is showing the diameter of the area of the detector. What we are using the APD of 0.5 mm. 0.5 mm diameter. So how it is changing as we are moving as we are increasing the steering range, as we are moving, let's say, we can say as we are changing the receiver position, we are decentering the receiver. So how the spot is going to change? So this is the coma kind of aberration. So that is why the collection efficiency is going down. And we checked for the illumination and communication performance also. So this is the illumination performance as we are increasing the decenting on the receiver, or we can say the steering. We can increasing the steering angle. So how the color of the light is changing? It is going towards the D65. These two photos these two images are for the spot. and how the collection percentage of the blue component and the lux level are changing. This is the communication system communication capacity performance. So we have done for the 1.25 and 1.5 Gbps, and we can see there is a good agreement between the simulation data for the collection efficiency and the BER performance, and these are the eye diagrams for that. So far what we have covered, like the LED based MIMO system, laser based implementation, and different white light generation techniques, and we have done this we use these two techniques in our lab to optimize the path loss or to steer the beam. So it will be very interesting to apply the experiment that we have performed in our lab to make the real-time products and applications. So we are open for the collaboration regarding to explore more in this field. So please do contact us if you are interested in this kind of work. And my colleague Satisha will be giving more, talk more towards the development side, like the USRP based real-time video transmission, video streaming, audio streaming, and the handoff and all. So thank you. And this is the future opportunities. So in real-time application, if we are implementing a laser-based VLC system, we are designing that. So to control the laser temperature, we need a current controller and temperature controller. That is a very big device. So the challenge is that if we want to a real-time product, so how we will miniaturize this circuit in a small box. And the another thing is, like, we are using the 50 mm diameter lens or 25 mm diameter lens, how to reduce the size of all these things to get the SAM performance. Another thing is, like, we are using like a discrete kind of components here, like the photodetector we are using, that is of very high speed, around 1.1 gigahertz bandwidth. So if we will reduce this size, if we will fabricate the photodetector on the PCB, so how can we achieve this kind of speed to make the system to communicate the system at a very high speed? So these kind of opportunities, future challenges are there. So this was all about what we have done at IISc in our lab under the guidance of Varun sir.
Okay, fine. Thank you, Fahim. So are there any questions for Fahim? You can type it on inside the chat box or raise your hand to ask those questions. I see one question. Can we say Li-Fi and VLC are same, or is there any difference?
Li-Fi is like we are using the product for the single product for the illumination and communication, but VLC is like we can use the communication only, the same product, or we can use the illumination also. So it is like a visible light communication. It is not talking about like whether we are using the product for the illumination or not. So this is the difference between these two.
Yeah, Li-Fi is more in line with Wi-Fi, right? Where it's not just the hardware, but the higher levels need to be defined as well.
It is just a replacement of the Wi-Fi product. So we will be using like Li-Fi instead of Wi-Fi.
Fine. Another question is, what is the maximum data rate possible as of now with the VLC setup we have?
In our lab, we are going up to 1.5 Gbps. We have achieved that with the on-off simple modulation, on-off keying modulation. And if you talk about the others work, so it can go beyond, like by using the single the RGB LED, it is going up to 15.73 Gbps. It depends like what link length we are using or what distance we want to communicate.
And what we have currently with OFDM and more advanced modulation, it can be pushed further as well, right? If you in the range of 1 to 10 Gbps is doable.
Yes, sir. So right now in our lab, we have implemented the QAM, OFDM bit loading and power loading also. So we have pushed the data rate up to 5 Gbps.
In the previous generation of mobile phones, right, there used to be infrared technology for personal communication, right, as an alternative to Bluetooth. right? Do you have any idea why it did not carry forward in today's smartphones? Or is there some way to have that as well?
So for infrared, it should be, I think it should be aligned, but for Bluetooth, it is not like the alignment problem is there, and the range is also matters.
I see. Okay. I guess the infrared technology was meant for more like short range, low data rate communication, right?
Yes.
Yeah. Yeah. Fine. Okay. Looks like that's okay. One more question. What is the maximum length achieved with the high throughput in general?
Maximum, like for high throughput, the people have achieved up to 1.5 meter with the data rate of almost 40 Gbps.
With careful attention to the optical path loss, what distances can be achieved?
With careful attention, just like we have achieved the 3 meter, if we will be using the high frequency component, like high bandwidth components on the transmitter side and the receiver side, if we will be using the RGB laser diode, we can also increase up to for a long distance communication. It depends on the what we are using on the transmitter and what we are using on the receiver side.
Okay.
What techniques we are using.
Okay, thank you. I think that's all the time we have for the questions for this talk. But I think there are few questions, Fahim. If you can type your answer in the chat box, that would be great.
Right, sir.
Okay, so I think Professor Abhishek is back. So I would request him to reconnect and then give his talk.
Sorry for the disconnection. Last time I didn't realize. So I will try and give the presentation now. Are my slides visible?
Yes.
So can you just let me know where I was? So
I think you had the multipath modeling and then some of the results you showed, right?
Okay, so
coherence bandwidth. I remember seeing the coherence bandwidth curve.
Yeah, this
slide 18, slide 19 also we saw. I think 20 is where you got disconnected. I think.
20. This one, right?
Yes, correct.
Can you also remind me of the time that I have?
You can take another 15 minutes. That's all.
Yeah. So, yes. So, yeah. So I was talking about this multipath VLC link, and I was talking that this delay spread is also a function of where the user is located in the link. So based on that, we can have a maximum value of the delay spread. So this is the maximum value of the delay spread if the user is in the worst location. And you can also have a minimum value of delay spread if the user is directly beneath an LED. So delay spread is a function also of the user location. For the designing purpose, we are focusing on the maximum value of the delay spread. And delay spread also translates to coherence bandwidth. So if you look at the minimum value of the coherence bandwidth, which is for the worst case, you can easily see that you can have a coherence bandwidth easily up to 1 gigahertz, the worst case coherence bandwidth. So that if you are designing a system of at around 100 Mbps, 200 Mbps, 500 Mbps, there should not be any problem, right? And the channel is good for that. So that is the main result from this work. Varun, I am still connected, right?
Yes, sir. Yes, sir. Continue.
Okay. So we can also talk about the BR performance of various modulation schemes. For this, we are focusing on a scheme. Yes, is there a problem? Okay, so we are looking at the BR performance. Just checking. Yeah, so we are looking at the BR performance. BR performance is also a function of where the user is located. And if we look at the maximum BR, that will be corresponding to the Maximum BR will be corresponding to the worst location of the user. Minimum BR will be corresponding to the good location of the user. So we also maintain quite a reasonable BR for simple on-off key modulation scheme for various data rates. And I will skip these slides for the time constraint and let us focus on the design requirements. These are really important parameters for designing a VLC link. So what it says is, if we have a maximum constraint on DR, let's say 10 to the power minus 4, and if we are choosing a room size of 10 meter by 10 meter, and if we are constraining ourselves to 10 milliwatt of power, then you can see that we can have a maximum bit rate of 0.9 Gbps with simple on-off key modulation scheme, right? The room size is bigger in this case, right? Earlier we were showing the simulations with 5 meter by 5 meter. Here we are showing it with 10 meter by 10 meter, right? So you can easily get up to 0.9 Gbps, the simplest on-off key modulation scheme. Of course, the LED semi-angle has to be 20 degree for this. Again, we can look at what coherence bandwidth is offered for the same requirements when the coherence bandwidth is around the same 0.96 gigahertz. Now, if we change the constraint, let us make the room size smaller, data rate also smaller, LED semi-angle as 35 degree. Then what we get is, if the user moves from the worst location to the good location, because BR is a function of the user location as well, then we can save on around 7 dB of optical power. And this is important. Why this is important? Because you can have a modulation scheme which looks at the user location and appropriately decides onto the decides the transmitted power based on the user location. So we can have modulation schemes in VLC like that, because a user is going to stay in a particular location maybe for hours, right? And so it is of no fun transmitting higher power when that user can actually work with the lower power. So from these results, we can get these kind of information as well. So this I will skip. All these slides I will provide, so you can read on to the slides and read on to the research paper. You can have various design requirements and design constraints that are possible in VLC link. This is the research paper that I am talking about. So if you have more questions on to this work, please read on to this research paper. Okay, now let us talk about the modulation schemes in VLC. So modulation schemes have to cater for flicker mitigation and dimming support. Flicker mitigation is easier. You can have run length sequences, and you can have 8 to 10 bit encoding and so on and so forth to mitigate flickers. Dimming is more challenging. Dimming means that we should be able to work with a reduced level of light, right? So for dimming, you can actually do the intensity variation at LEDs, which is not recommended because they can be chromatic shifting. It leads to lower efficiency in drivers and things like that. So people have been focusing on digital dimming, which basically caters to the change in the duty cycle of LEDs. So let us look at the two modulation schemes, variable on-off key. I will explain this in a little bit more detail, and I will skip the remaining. So for example, if we look at the normal on-off key, data is being transmitted for 50% of the time as 1, and data in the remaining 50% of the time is 0. And we basically transmit some power for bit 1 and no power for bit 0, that is on-off key. Now suppose we want to reduce dimming below 50%, what can we do? So let us look at this picture D. So for bit 1 in on-off key, we have the transmitted power for all the time, but here even for bit 1 we have certain time period for which there is no data, and hence the average will be less than 50%. If you want to increase the average more than 50%, let us look at this part A. So we can have dummy data which can fill in for bit 0 as well, right? So there is this dummy data in bit 0, and there is dummy data in bit 1, and actual data is only this. So the average will be increased more than 50%. So this is typically what is variable on-off keying. You vary the width of the pulses in bit 1 and bit 0 based on the dimming requirement. Okay. So similarly, we can extend the same idea to variable pulse position modulation as well, right? I won't explain this again in detail, but you can have again the same situation where the pulses have different widths depending upon the dimming requirements. So you have other options as well, but these options are more complicated and hence they are not recommended by the standard. We have MPPM and OPPM, which are a little bit more complicated to implement. So let us look at the power spectral density. We have calculated this in this journal, which you can read again, and we have looked at the power spectral densities of various schemes. In this case, we are looking at VOK, and we can also look at the power spectral density of variable PPM. It also depends upon the dimming factor and so on and so forth. We have calculated the bandwidth requirement and DR for various modulation schemes as well. This picture is slightly interesting. What it shows is that DR is the smallest when the dimming factor is 0.5. If dimming factor increases or decreases, DR has a penalty. We have a penalty to pay. We have to have higher transmitted power. And this holds true for both PPM and OK, the variable versions of these. You can reduce the BR by having a zero forcing channel equalization or other equalization. For this work, we have used zero forcing equalization. And what we show is that we can reduce the BR by using this zero forcing equalizer. So these green curves are zero forcing equalizer, red curves are with no equalization. And you can see that we can reduce on to the BR by having this ZFP. So multiplexing techniques, we can use NOMA in VLC. NOMA is my favorite to be used for visible light communication. It increases the spectral efficiency and doesn't have a lot of trade-offs. And MIMO we cannot use because MIMO requires the channel to be uncorrelated, which is not the case in visible light communication. Okay. So I won't go into the details of NOMA, but NOMA basically means that to different users, we are transmitting different power levels, right? And how do we select these power levels? Based on the channel coefficient for different users. A normal idea is that this is different from water filling. In water filling, what we do is, if the channel is bad, we transmit less power onto that channel. Here, the idea is different. If the channel is bad, you try to compensate for that by transmitting higher power. Okay, so the power allocation is a function of the channel channel of the user. Okay, an important point is that if you sort the users in the ascending order of their channel gain. So for example, H1 is the lowest, right? So that means the P1 should be the highest, right? That means P1 is the worst user. It's located at the edge of the cell. Okay, so power for the channel 1 should be the highest, right? So what we propose is the power allocation coefficient. Power allocation coefficient means if the users are sorted in a certain order, then how does the power vary compared to the previous user in that ascending or descending order, in whichever way you are sorting. So I won't go to the details of this, but what we have shown is for the fair power allocation scheme, that means for each user to get the same BAR, this should be the power allocation factor that can be used in the VLC. Okay, so this power allocation factor will ensure that every user is going to have the same BAR performance. And we compare it with other schemes, state-of-the-art schemes, and we show that our proposed schemes are better in fairness in both bit error rate and in throughput. Okay. So in the last few minutes, I will present the demos for these slides. So this demo is in IMC 2019. So here we are showing how to transmit the video signal over the Li-Fi transmitter and receiver. So this is a Li-Fi transmitter, this is a Li-Fi receiver, this is a transmitted video, this is a received video. So let us see this. The video is correctly received at the receiver, and if you block this video by creating a shadowing effect, then the video stops. So let us look at the received video, and when we remove the blockage, the video resumes. Okay, so this demonstrates the right working of Li-Fi link. This was demonstrated in IMC 2019. Now let us do the same experiments over USRP. So what we are targeting is a data rate of around 20 Mbps over Li-Fi link because we are using white LEDs. So this is done over FPGA board, and we can transmit the video from one end to another end faithfully without any distortion. And the third demo that we are working on is the lens design for the VLC link. The lens should focus the light received from various directions correctly onto the photodiode. In that case, we are developing a lens system which is tracking the input light source. So as you can see in this video, I will play this out again. This light sensor is tracking the mobile phone because mobile phone is emitting the light, and based on where you orienting the mobile phone, the lens system is also moving in the same direction. So this helps us to focus the light at the center of the photodiode. So this completes my presentation. Thank you so much. Thank you, Varun, and thank you, organizers, for inviting me for the talk. If there are any questions, I will be happy to answer.
Okay, thank you, Abhishek. So if there are any questions, please put it on the chat box or raise your hand and you can ask the question. So I have a question. The last slide you showed, right? The tracking. How is the feedback set up from the cell phone to the transmitter?
So basically, that has a light sensor, and the input of the light sensor is set to Raspberry Pi, and it has a motion sensor also. So based on that signal, it's tilting the mobile phone, to the camera sensor in one or the other direction. It's a Raspberry Pi based module.
Okay. Any other questions? So in the Indian context, do you see certain use cases which are emerging for VLC or VLC combined with RF or any of these things which will find immediate use?
I am hopeful and optimistic for that. That's why I'm researching it. Mm-hmm. So yes, I think that VLC will pick up, maybe not immediately, but at least in 5 or 6 years from now. And I think VLC will be quite a big contender for 6G whenever it will be rolled out. And I'm very optimistic that this will eventually replace Wi-Fi in the long run. So that's what I hope. So yeah, when will this happen? That's not clear to us, but yeah, it will definitely happen. So I got completely excited when I hear from you that you are transmitting 1.5 Gbps or maybe 40 Gbps over Wi-Fi. So all these results are very encouraging.
Yeah. One more question: is the tracking optimized to deal with ambient light or other unwanted sources?
Yes, so cancelling out this ambient light is easy because this is a constant light, so we can have 2 photodiodes. And in one photodiode we can have a signal plus ambient light, and in another photodiode you can have ambient light. So then you can make a simple circuit which cancels out the ambient light because it's coming onto both photodiodes. So it's what is done in this balanced photodetector which cancels out range effect. Very similar to that.
How can we switch between RF and VLC to provide guaranteed communication, and how to build a hybrid transmitter?
We are not working onto that, but I can still answer that question. So basically, it depends upon what you want to do. So suppose if you want to offload your RF signal to VLC network whenever the load on RF signal increases, then you can calculate the load in the network, and whenever you see that the load crosses a certain threshold, you activate some of the VLC nodes, or you can activate the VLC nodes if you can sense that the nodes are quite stationary and there is a direct line of sight path available to a receiver. Then you can activate VLC for those nodes, or if you want to offload the load from one network to another, I think that can be done using an appropriate MAC protocol. That should not be an issue, and a lot of people have been researching on that.
And when we merge VLC with other communication modes such as RF, FSO, does it dominate on them? in case of dual hop or multi-hop or hybrid systems?
Sorry, Varun, can you repeat the question? I didn't understand this.
When we merge VLC with other communication modes such as RF or FSO, does it dominate on them? I'm assuming that does RF or the optical dominate over the other, that it can create interferences, or I assume that
Actually, we have a project at IIT which is known as NICNet, Next Generation Indoor Communication Network. In that, we are working on merging this RF, VLC, and FSO, all three technologies together. And we are, with merging that, we mean that we select the optimum technology for a certain situation. For example, as I've said, if we have a direct line of sight path from the transmitter to the receiver, then we use VLC because that would be best. And if the user is not located in line of sight, if it's moving out of the room or if it's going into the shadow regions, then we activate RF. And all these technologies have different advantages and disadvantages. So I don't think one is dominating over the other. It is each technology should be used whenever it's most advantageous to use it. So if you can have certain nodes that doesn't have VLC communication, for example, if you want your computer to be connected at very high speed, let's say 20 Gbps or 40 Gbps, 50 Gbps directly under a transmitter, you can make that link using an FSO communication. So each technology has its advantages and disadvantages, and it is not that one technology is going to dominate over the other. It is, in my opinion, it is about making use of the technology whenever it is most apt to do it. Because till now, so far, we haven't get rid of all disadvantages of VLC.
Okay, thanks. Looks like that's all the questions we have. So I would like to take this opportunity to thank Professor Abhishek once more for the interesting talk and also the demos he showed at the end, and also to thanks to the audience also as well to ask all these questions. And sorry about the technical snag, but hopefully things were back to normal after that. So thank you again, Abhishek.
Thank you, Warren. Thank you all. Thank you for attending this talk.
Thank you. And the last talk here will be given by Satish Ramachandrapura. So he's a PhD student, and he'll be talking about more of the system level testbed implementation we are doing at IISc in the context of VLC links. Satish, over to you.
Yes, sir. Hello, am I audible?
Yes.
Yeah. I shared my slides. Is it visible?
Yes, go ahead.
Yeah. Is it in full screen, sir?
Yes, go ahead.
Yeah. Good afternoon, one and all. This is my last talk in the context of system level implementation and VLC RF handoff in this webinar. Myself, Satish Ramachandrapura, working as PhD student in ECA department, IISc, under the guidance of Varun Raghunathan, sir. My colleague is Fahim Ahmed, who has given the previous talk. Here is my outline of the talk. I'll give the introduction. You had many introductions from other speakers. I'll introduce what is the need of VLC in 5G networks. And next, I'll talk on 4 interesting use cases, like the data streaming over VLC in unidirectional and bidirectional cases, and VLC RF coexistences. So many of the questions were from these sections, like how do we merge VLC and RF together, and handover requirement in the context of VLC. And last talk will be on some emerging technology, that is energy harvesting in VLC, and some concluding remarks, and finally we'll have the question and answers. As you have heard from many speakers with the previous knowledge, like visible light communication is a new technology, upcoming technology, which provides illumination and communication together. So it is predicted that in the near future, wireless user will spend more time in the indoor scenario and less time in the outdoor scenario, like 80% indoor and 20% outdoor, because most of the communication gadgets are with us and we are inside the building. So it is a requirement, like we need illumination inside and also the communication together. So VLC is a good technology which provides both. And you have we have the bandwidth requirement. We have the bandwidth requirement more in the upcoming technologies, and VLC offers the more bandwidth, high bandwidth, and it is like 10,000 times the larger bandwidth compared to the RF spectrum. So in picture you can see that many of the applications, picture number 1, which is depicting you the office environment with most of the users in mobility with their gadgets, and second one is localization application in an office or some mall, and third application is very important in a office, a hospital environment for telemedicine kind of application, where the doctors can see the video of the operation that is going on, where thereby we require more bandwidth of utility in that scenario. Coming to the VLC or Li-Fi application areas in the upcoming technologies like 4G, 5G, and so on. So the upcoming technologies requires higher data rates greater than 100 Mbps and decreased latencies like less than 10 millisecond. So VLC is one dominating technology which provides such higher data rates like greater than 100 Mbps, reaching up to tens of Gbps, and reaching the latency to a low level like 1 millisecond. So here we find most of the interesting applications like robotic telepresence, multi-person video call, virtual reality, tactile internet, etc. So this will be a interesting area of application of VLC. So coming to the commercial Li-Fi devices available. So basically Harald Das, who is the father of Li-Fi technology, with his trademark like Pure Li-Fi, their company has developed some of the gadgets. So we, in the context of Li-Fi technology, we require the transmitters from the ceiling end. I mean, if it is an indoor application, we require illumination from the ceiling end and devices at the floor end. So like the end applications like the laptops with the integrated Li-Fi technology, which you can see in the picture A, and a mobile phone case. Normally we'll have the RF technology receiver in the mobile, and these people are coming up with the Li-Fi technology add-on as a mobile phone case in the mobile scenario. And as a ceiling, seal side, that is the transmitter side, we have pendant lights which are transmitting as well as illuminating, and there is a commercial device called integrated luminaire which provides illumination and communication also. So having these gadgets, where do we use? So this is a very interesting application like mobile telepresence robot. So basically it's a robot with video conferencing steerable from the remote locations. These can be used for telemedicine application from a doctor's end or hospital emergencies. So they are basically built with multimedia applications like high quality cameras, high quality streaming requirements. So here is a set of commercially available mobile telepresence robots. So you can see the bandwidth requirements for them and the lack of any other commercial network technologies. You can see that all these commercially available mobile telepresence robots are available only with the Wi-Fi technology, and they require higher bandwidth. So if we, the concept like the commercial Li-Fi technology, if we can adopt in these telepresence robots, so they can work with Wi-Fi as well as VLC, and they can be more robust in usage. So now I'll talk upon the data streaming through VLC. What are the current works that are going on, and what is the work that is going on from our end. So this is a simple work on design and implementation for a USRP based visible light communication transceiver. So in this you can see in the pictorial picture where they have the lab setup with the light being transmitted which carries the information. They used a USRP for up conversion and down conversion. So they achieved a data rate of 2.5 Mbps with 10 power minus 5 BR. And you can see that they tried for two data rates in the curve. You can see like 2 Mbps and 2.5 Mbps. So as they increase the distance between the transmitter and receiver, the data rate, BR has increased. So we can fix a particular distance and we can operate the system. That's what the understanding from this work. So next I'll introduce you our work. As my colleague Fahim has introduced the hardware level setup, this is the setup here shown. And with this, we developed a system level setup. To recall, we have a laser source, which is a blue laser, and we converted it to white with the remote phosphor. And we have an aspheric lens to converge and focus towards the receiver. And this is the receiver, the APD with a aspheric lens. And we have the RF data source, bias T, and the received data can be analyzed with the DSOs. So we observed that the bandwidth of our system is crossing 800 megahertz with 3 dB bandwidth, and our team has measured the data rate up to 1.5 Gbps with OK modulation. With this setup, we tried for a video streaming over this link with the help of USRPs. Here is a simple block diagram of the same. You can see the pictorial representation of our lab setup with two computers, two USRPs, and a unidirectional link here in the diagram. So the block diagram will explain you what is going on. So first we have a video LAN player in our transmitting end. So we streamed a high quality video, and we tunneled that in using the UDP protocol. And from the USRP end, we up converted it to the bandwidth of transmission over the laser bandwidth, which we have seen the laser bandwidth in terms of 100 to 800 megahertz. So the output of USRP is fed through the RF amplifier, which matches the required gain level to drive the laser diode. So from the laser diode, we are getting the blue light, and that is converted to white using the remote phosphor, and it is passed through the aspheric lens to focus towards the receiver end. So we have a photo detector with the aspheric lens, and the received light is converted back to the electrical domain, and it is down converted using the USRPs. And decoding and downlinking is done in the system, and we could able to play the received video using the video LAN player itself. In the next slide, I'll explain you about what is the kind of video streaming we tried. The quality of the video was a HD 1280 x 720 with 60 frames per second, very high quality video. And we used the 16 plus 16 IQ samples, which is like 32 bits per sample. We used a GMSK modulation. Throughput of the video was 12.5 Mbps. In the right side, you can see the video quality in terms of quantitatively, like we captured the scenarios of transmitted and received video. They look good in terms of the pictures, and also we tried to measure the quality assessment using a method called frame loss statistics. I listed out the few records in the table where we try to increase the transmitted power and measure the frame losses over 10,000 frames. It is observed that the frame losses will decrease as we increase the optical power, and it is optimum in a frequency of center frequency of operation over the USRP device. Next, we tried for a bidirectional video streaming. Usually a VLC link, we think like a downlink. There is another opportunity to make it as a bidirectional using uplink also. Basically, the downlink in an indoor scenario, which is from floor to the ceiling, which is a illuminating one. We need the illumination and communication. For the uplink, which is from the gadget to the ceiling side, which is not to be illuminated. So we may go for a IR based if we are strict to bidirectional VLC, or we can use the Wi-Fi technology or any RF technology for the uplink. But here we focused on the pure VLC technology where both the links are VLC only. So in this case, this is the model. Model which we used. We had two computers and two USRP devices which have two TX-RX, and in the downlink we used the laser source which is generating blue light and converted to white light, which is illuminating as well, and we used the photo detector for the detection, and in the uplink we used the IR source and the detector. So this this constitutes the complete bidirectional video streaming. In my next slide, I'll demonstrate you with a simple video how the setup works. This is the block diagram of the system, which I explained just now. Yeah, here is the complete lab setup what we have with the two USRPs in place, and this is the complete VLC link what we have. So the left to right is the uplink and right to left is the downlink. I'll explain in between as the video goes on. Yeah. So you can see the streaming videos, two different streaming videos in two different computers. They will be explained in parallel. So this is our downlink. Blue light is generated using the laser, and that is converted to white using the remote phosphor and passed through the aspheric lens. And at a 2-meter distance, we have the receiver. And these are the USRP devices with earlier we had basic RX and basic TX as the data cards. So this is our APD photo detector to detect and convert it to electrical domain. And now you will see the HD quality video which I described. So this is streamed from the downlink, and we are seeing it in the receiver side. And this is the uplink part where we have a IR source, and it is streaming the other video. You can see, you can have a vision like it is streaming from floor side towards the ceiling side. Yeah, this is another USRP which is receiving. And this is our detector. So this complete setup contributes the bidirectional videos system. And now you are looking for the streaming, and we'll demonstrate you two scenarios where we will strike the light, we'll cut off the light, and the streaming stops. Yeah, this is the scenario where we'll strike the light, and this is the scenario with ambient light. You can see the streaming still continues. Yeah. Yeah, that's about the work which we tried for bidirectional and unidirectional video streaming. So next talk is on, next topic is on RF VLC coexistence and handoff. So the 5G is focusing for is the slide getting changed? Hello, sir.
No.
I moved to the next slide.
Can you come outside slideshow and go back again?
Yeah. Wait.
Yeah, your first slide is visible.
Yeah, I'm sharing it again. Sorry. Yeah. I think this slide was not visible. It was about RF VLC coexistence and handoff. So basically, to introduce VLC into any of the upcoming core technology like 5G or 6G, they work with RF technology, and to introduce this as an RDAN, they should coexist. Here is a model referred from this paper, the VLC visualization in a 5G network. As Professor Chokalingam sir said, so VLC network is termed as auto cell. So in an auto cell, RF and VLC should coexist. So I'll explain you why. VLC covers some of the gadgets inside the indoor application, and RF covers some of the gadgets. So let's look at which technology is referred. Like RF technology has always associated with the EMI, the electromagnetic interference, and in some scenarios like medical devices, malfunction caused by the RF devices, wireless devices, due to the EMI. So we should get rid of this, and RF solutions are reliable and have broad coverage. So RF has its own advantage of broad coverage and allows higher mobility. Looking at the VLC, we have seen most of the advantages from the VLC, like it is supporting us higher data rate for the multimedia video transmission and directional transmission for a relatively static user, like in an office user is sitting and he's consuming more data at a sitting place. So in such scenarios, we can club together, like a user may be using for a long hours over the VLC link and started moving, and there is no coverage from the VLC, then RF should support. So this is how the coexistence should work, then they should work together. And in Michael Raham's paper, he described the concepts and opportunities and challenges for coexistence of Wi-Fi and Li-Fi together in a 5G environment. Here is the system which he had shown, the VLC downlink. Why we prefer the downlink as a VLC is it provides the higher data rate, and most of the time we try to downlink the data rather than uplink it. And Wi-Fi uplink, and we have a wired cable to cater the access points. So this is the scenario which he explained, and there is a diagrammatic picture of the same. Like he described it in two methods. One is called hybrid technology, and the right one, figure B, is the aggregate system. In the hybrid technology, you can see that optical wireless channel, which he is referring, is providing only the downlink, and RF technology is providing both uplink and downlink. So the measurement, the advantage of this is explained in the graph. I'll explain it later. And the figure B is aggregate system, where VLC is providing both uplink and downlink, which we referred it as bidirectional VLC, which we explained in our work. And RF is giving you both uplink and downlink. So with this concepts in mind, they they tried to measure the data rate with the distance as the varying parameter. So it is observed that if we are using the Wi-Fi only technology, which is blue line in nature, and it is observed that as the distance is moving, since Wi-Fi covers a larger area of coverage, and average data rate remains the same. So, and in the second technology, that is hybrid technology, which he proposed, so it provides higher data rate compared to the Wi-Fi only technology, and over a certain distance it's started decaying because VLC coverage is no more, and it comes down, which is catered by the Wi-Fi technology. Now if we go for an aggregate system where uplink and downlink are provided by the VLC, where we can achieve the higher average throughput. So this is the concept towards an aggregation of VLC and Li-Fi together in future. So this is another
time check. You have about 8 minutes.
Okay, sir, fine. Here is another work by Michael Raham. So where he introduced a hybrid technology, where he has a multiple VLC hotspots, and there is a RF router, RF access point. So basically, so most of you have asked how do we connect both. So there will be multiple VLC points. They are nothing but the lighting spots in our indoor scenario. And if you look at the illumination scenario, so they will cover a certain range, and there will be certain range which are, region which are uncovered in the indoor scenario. So where RF comes into picture is where the device is moving and it has to be catered with the data. So their RF caters the data, and the coverage will become seamless. So that is the significance of mixing or hybridizing the RF and VLC system together. Some plots are shown, like Wi-Fi technology alone, or VLC with 4 access points, hybrid with 4 access point, and hybrid with 8 access point. In this, you can see that it can start supporting more number of streaming users when there are higher number of hybrid systems with more number of access points from the VLC side. So to start with this hybrid technology, we started with a simple experiment on handover and coexistence experiment. So this is the model we have. We have a USRP access point, USRP based VLC access point, and USRP based RF access point in hand. And we developed a dual receiver model which can simultaneously receive RF data as well as VLC data. In this context, we tried to transmit same videos from both the access points, and try to receive from the dual receiver model. So here are the scenarios which we created. Like scenario number 1, when the dual receiver model is under no coverage, like it is kept away from both of them. And scenario number 2, where we are entering into RF, and scenario number 3, where we are entering into VLC network. I'll explain you this with a video demonstration now, which we tried in our lab. I started playing. Is it visible?
Yes.
Yeah. So this is the block diagram which I explained. And now I'll show you, this is the RF USRP access point, which is streaming this video. And this is our VLC link. You can see the video stream. Yeah. This is the scenario 1, where you are seeing no video getting streamed in the dual receiver model, and you can see there is a USRP sitting on the table, which I am referring to dual receive model. And now we'll start moving the receiver towards the VLC link, and the receiver starts receiving it. Video started streaming. And scenario number 3, where we are moving away from the VLC link, that is, we'll lose the line of sight, and we enter into the edge of RF link. So again, the video from the other source started streaming. So this trying to develop a coexistence protocol, like measuring the RSSI from both the VLC and RF access point, depending on whichever is whoever's RSSI is larger, we register to that particular access point and continue the data transmission. And in a call flow for RF to VLC handover, we have multiple entities, like there is a data source, there is a VLC access point, RF access point, and our mobile terminal is dual in nature with VLC downlink, RF downlink, and RF uplink. So first, if you take a scenario like there is a data streaming that is happening from RF access point, and now if the mobility is from RF access point to VLC access point, we should continuously monitor the RSSI measurement and send it to the data source, and it will make a suitable decision based on the measurements made, and a handoff initiations will take place, and on successful handoff, it will forward the data packets from RF to VLC access point, and the streaming continues. This is what we try to implement soon. So this is about the another call flow for VLC to RF handover. This is similar to the previous explanation. That's all about RF VLC coexistence. The next work is on energy harvesting in VLC receiver. This is the interesting work towards the VLC aspects. So this will be more focusing for VLC receivers which are having energy thirsty, like they don't have the energy in the receiver, like a VLC sensor node which is not catered by the external power, which has to generate the power from itself. So since we have the illumination from the source, and we have the solar panel which can harvest the energy, can we club this concept of energy harvesting in the receiver so that we can cater the harvested energy to drive our receiver? So in this context, we go for a new concept like energy harvesting, or by the name called self-powered VLC receivers. So basically, we use the photodetectors as the receivers, which have faster time response, and but they require external power and convex lens for converging. And if you look at the solar panels, which support the lower data rate for a sensor application, and which also harvest it with the larger receiving area, and which does not require external power. So in this context, if we go for a energy harvesting, we can serve the sensor node with the self-generated power. So in this context, there is a work going on by Boone Osai and team. So they worked on this kind of laboratory experiment. They demonstrated it, like so they created a 20-meter length link with the white light being generated from the laser. They tried to capture it from a solar panel, thin film solar panel. The energy harvested from this solar panel is catering the receiver circuit and driving the receiver circuit. Thereby, there is no external power that is required. So in this context, the right side figures indicate their actual work, pictorial representation. And in the graphs, you can see that there are two graphs, A and B, where they try to measure the power maximum developed. The A refers to only one device, one solar panel, and figure B refers to 3 solar panels. You can see the power maximum developed from the solar panel increases with the number of cells that are attached. Like they developed 474 milliwatts, which can cater their receiver circuit. In this context, we are moving towards planning to work on this area also, where we are trying to use the solar cell as well as photodetector to extract the energy and drive our photodetector from this with the lens combination. So to conclude, I talked upon the video streaming or multimedia streaming over the VLC network in bidirectional and unidirectional cases, and also touched upon RF VLC coexistence for the upcoming technology so that we can push VLC into the 5G technology, and a concept like for IoT devices or sensor devices, how VLC can support the energy harvesting concept. So this is about the talk what I had, and in the future scope, integrating this with the 5G standard environment will provide the ease of switching between the RF and VLC. So if we can develop a protocol, some layers from the 5G standard like open air interface, this is the interesting area where we can work on. And as my colleague Fahim said, if we can miniaturize the device and make them handheld, so and make the prototypes of that, that is one interesting area to converge all these topics into one. That's about from my side. Thank you.
Okay, thank you, Satish.
Yes, sir.
Yeah, if there are any questions, please post it on the chat box or raise your hand. Okay, we are running a little over one. Okay, there is one question. Ankit, you can please unmute yourself and ask the question.
Yeah. So good afternoon, everybody. So I have just a query, like when you set up this for VLC transmission, the block diagram that you showed, and you had this USRP. So
yes,
at what frequency you are operating the USRP, like after up conversion, like can you just
Yes, sir. Yes, sir. We had earlier in the work what we shown, we had the basic TX and basic RX data boards where they support up to 250 megahertz of center frequency. We tried to stream at the center frequency of 240 megahertz. That was the trial we had it from them, and later we upgraded them to UBX kind of data boards. Now we are trying to stream over that, like 2 gigahertz, 2.4 gigahertz, etc.
Okay. And that laser source you used, right? There was one laser source. So may I get the specification or some details later on? Not now.
Yeah, definitely.
Yes.
We are using 785 nanometer blue laser and another IR laser.
450, right? 450 nanometer.
Sorry, 450 and another one IR laser.
Okay. So just a final question, like, so do you think like when you are talking about the visible light communication, indoor visible light communication, we should use this laser kind of sources, or right now you are using for experimental, then you will switch to LEDs or some like?
No, our team focus is on laser based to achieve the higher data rate. And as my colleague Fahim talked about this MPE levels, so we are trying to reduce the power transmission so that it is far below the MPE level. So that is eye safe as well as human safe. So that's the constraint we have, and we focus on laser based.
Okay, thank you. Thanks a lot. Thanks. Wonderful talk. Thank you.
Okay, thank you. So if there are no questions, I just had few concluding remarks about how you can reach us, or how you may want to make use of some of the facilities we have. So let me please, I will just share my screen. This will be just 1 minute. I hope you are able to see my slides. So as you have seen from some of our talks, we have developed enough expertise in this project on optical characterization, the optical hardware, ray tracing simulations, the test equipments which as part of this project, system level hardware like the software defined radios and the analysis software and so on. As part of this project and our responsibility to give back to the community, we feel that we have to obviously have potential users from outside, especially industry and academia, who can collaborate or make use of some of these facilities. And we are trying to set up a model where this can be done. And if there is particular interest in using our facilities, please do drop an email to us in the 5G testbed email ID, which I've given here. You can also find more information in our 5G testbed website. So if you just do a Google search on 5G testbed and IISc, you can easily go to this link. Right? And also when you send out email, please be specific on the topic of interest and what infrastructure you would like to utilize. And then we can set up more focused discussion with you to see how we can make that happen. Right? And with that, I would also like to acknowledge the funding agency, the Department of Telecommunication, DOT, who helped us build this VLC testbed. We'll also like to thank the ECE department where this testbed is being hosted, and also the 5G testbed team, the principal investigator, Professor Chandramurthy, and Dr. Sudhakar, who helped us with this webinar, and also as a project manager for this project, and also Ashish for helping us set up the posters, the meeting link, and so on. And two of my PhD students, Fahim and Satish, who presented in this webinar, and also the invited speakers who were kind enough to share their wisdom as well. And I would also like to thank all the attendees for staying a little bit late as well, and then asking all these interesting questions. Right? And I would like to thank you and stay safe. And we also look forward to hearing from you about any future collaboration possibilities. Right? Thank you very much, and hope to see you soon in the next webinar. Right? Thank you.
Thank you, sir.
Yeah.